ಹಾ ಹೌದಾ? ನಿಮ್ದ ಅಲ್ಲಿ ಇದು ಏನಾರು ನಿಮ್ದು ವಾಲ್ಯೂಮ್ ಇದು ಸ್ಪೀಕರ್ ಏನಾರು ಮ್ಯೂಟ್ ಆಗಿದ್ಯಾ ನೋಡಿ ಸರ್. ಹೌದಾ? ಹಂಗಾರೆ ನಿಮ್ ಸ್ಪೀಕರ್ ಏನಾದ್ರು ಮ್ಯೂಟ್ ಆಗಿರ್ಬೇಕು ಸರ್. ಇದ್ರಲ್ಲಿ ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ ರೈಟ್ ಸೈಡ್ ಅಲ್ಲಿ ಒಂದು ಸ್ಪೀಕರ್ ಐಕಾನ್ ಇದೆಯಲ್ಲ. ಹೌದಾ? ಅದಿದ್ಯಾ? ಓಕೆ ಸರ್, ಮತ್ತೊಂದ್ಸರಿ ನೀವು ಹೊರಗಡೆ ಹೋಗ್ಬಿಟ್ಟು ಮತ್ತೆ ಜಾಯಿನ್ ಆಗಿ ಸರ್. ಮತ್ತೆ ಓಕೆ ಸರ್, ಹೊರಗಡೆ ಹೋಗಿ ಜಾಯಿನ್ ಆಗಿ ಆಮೇಲೆ ಪ್ರೆಸೆಂಟ್ ಮಾಡಿ ಸರ್. ಹೊರಗಡೆ ಹೋಗಿ ಜಾಯಿನ್ ಆಗ. ಓಕೆ ಸರ್, ಪ್ಲೀಸ್ ಸರ್, ಹೊರಗಡೆ ಹೋಗಿ ಮತ್ತೆ ಎಂಟ್ರ್ ಆಗಿ ಸರ್. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
Students, it's a small technical glitch. Kindly bear with us. It's hardly another 1 minute. So sir will be coming back. Small technical glitch from the system end. Okay. And the students, as far as the video is going on with its process, we will not be having much of the time to have revisions. Reason is from June 15th, final year examinations are getting started, theory examinations, followed by their practicals, because they'll have only one practical, that is project viva will be there after their theory. Once that's completed, they'll be calling for the lower semesters like 6th and 4th for examinations. Maybe from June 15th you are permitted to come to the classes, right? So if you are really interested, those who have some doubts in getting the concept or principle, some clarity, please call back your class teachers. The intern they'll come to the department, and we talk to principal, and we see that you are allowed into the college. We will be conducting classes. We are not going back, or we are not hesitant. In spite of doing all efforts on online classes, we teachers are ready to take offline classes 1-to-1. Why I am telling with confidence is, yesterday about 10 of 6 semester students had come. Your seniors had come. They gave a request to me, and I in turn spoke to principal, and he has permitted. From Monday they are attending classes, 6 semester class, about 10 or 12 who are lateral entry students. Because of network connectivity, they could not understand, and hence they are coming. Likewise, if you are interested, few of you make a call to your class teacher. They'll in turn approach head of the department, and we'll make arrangements. We teachers are ready with all the material and stuff. We are ready to teach you offline, maybe for about 10-15 days, every day about 2 hours or 3 hours, depending on your compatibility or convenience and our work schedule, because even we have works at the college. Reason is from June 1st, first internals, third internals are starting. With that validation should be there. Finalization.
ಗೊತ್ತಾಗ್ತಾ ಇಲ್ಲ. ಅವ್ರು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. ನೀವು ಮಾತಾಡೋದು ಫೋನಲ್ಲಿ ಕೇಳ್ತಾ ಉಂಟು. ಅದೇ ನೀವು ಮಾಡೋದೇ ನಾವಿಲ್ಲಿ ಏನು ಅಲ್ಲೇನಾದ್ರು ನೀವೇನಾದ್ರು ಮಾಡ್ಲಿಕ್ಕಾಗ್ತದ? ಇಲ್ಲ ಅಲ್ಲ, ನಾನ್ ಮಾತಾಡೋದು ಕೇಳ್ಕೊಳ್ಳಿ, ಹೋಗ್ಲಿ, ಪರವಾಗಿಲ್ಲ.
ಸರ್ ಕೇಳಿಸಿದೆ ನಮಗೆ, ನಮಗೆ ಕೇಳಿಸಿದೆ.
ಇವಾಗ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡಿ.
ಪ್ರೆಸೆಂಟ್ ಮಾಡಲಾ? ಪ್ರೆಸೆಂಟ್ ನಾವು
ಎಸ್ ಸರ್, ಸುರೇಶ್ ಸರ್.
ಸಿದ್ಧ ಸರ್,
ಎಸ್ ಸರ್. ಆಡಿಯೋ ಇನ್ನೂ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಅಲ್ವಾ ಸರ್?
ಸುರೇಶ್ ಸರ್ದು ಅನ್ಮ್ಯೂಟ್ ಆಗಿ, ಅದೇ ಅವ್ರದ್ದು ಅನ್ಮ್ಯೂಟ್ ಆಗಿದೆ.
ಅದೇ ಅನ್ಮ್ಯೂಟ್ ಆಗಿದೆ,
ನಮಗೆ ಕೇಳಿಸ್ತಾ ಇದೆ ಅವ್ರು ಮಾತಾಡೋದು.
ಅಲ್ಲ, ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡಿಲ್ಲ ಅವರು, ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡಿಲ್ಲ.
ಇಲ್ಲ, ಆಗಿದೆ ಸರ್, ಅನ್ಮ್ಯೂಟ್ ಆಗಿದೆ. ಕೇಳಿಸ್ತದೆ?
ಎಸ್ ಸರ್, ಕೇಳಿಸ್ತದೆ. ಕೇಳ್ತಾ? ಓಕೆ,
ಕೇಳಿಸ್ತಾ ಇದೆ.
ಆದ್ರೆ ನೀವು ಮಾತಾಡೋದು ಕೇಳಲ್ಲ, ಅದೇನೋ ಇದಾಗಿರ್ಬೇಕು ಮೋಸ್ಟ್ಲಿ. ಇರ್ಲಿ, ನನಗೆ ಹೇಳಿ, ಅದಾದ ತಕ್ಷಣ ವಿಶ್ವನಾಥ್ ಅವ್ರು ಮಾತಾಡ್ತಾರೆ.
ಹೌದಾ?
ಹಾ ಸರ್, ನೀವು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಿದೆ ಸರ್.
ನಾನ್ ಮಾತಾಡೋದು ಕೇಳುತ್ತಲ್ಲ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲಿ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್, ಕೇಳಿಸ್ತಾ ಇದೆ.
ಸರಿ ಸರ್, ಅವ್ರು ಮಾತಾಡೋದು ಕೇಳುತ್ತೆ.
ಅದು ನೋಡೋಣ ಸರ್, ನೀವು ಸ್ಟಾರ್ಟ್ ಮಾಡಿ ಸರ್, ಅದನ್ನ
ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಅವ್ರದ್ದು ಆಯ್ತಾ?
I think HOD sir has actually spoke to
ಆಯ್ತು
students.
ಆಯ್ತು.
ಓಕೆ ಸರಿ.
Students, now we will be having Suresh sir Vayar to taking over the screen. I'll join at the end, okay, because some technical one way there's a communication, so please be silent.
Yes sir, thank you sir.
Thank you sir.
Suresh sir, you can start sir. ಅವ್ರಿಗೆ ಕೇಳಿಸಿಲ್ಲ.
ಇಲ್ಲ ಅವ್ರಿಗೆ ಕೇಳಿಸಿಲ್ಲ, ಫೋನಲ್ಲೇ
ಹೇಳ್ತೀನಿ ಸರ್.
ನಾನು ಹೇಳ ಸರ್?
ಹೇಳ್ತೀನಿ ಸರ್, ಮಾಡ್ತಾ ಇದ್ದೀನಿ.
ಹಲೋ, ಅವ್ರದ್ದು ಆಯ್ತಾ? ಓಕೆ, ಅವ್ರು ಏನ್ ಹೇಳಿದ್ರು ಪಾಪ ನನಗೆ ಗೊತ್ತೇ ಆಗ್ಲಿಲ್ಲ.
ಇಲ್ಲ ಸರ್, ಏನಿಲ್ಲ, ಸ್ಟಾರ್ಟ್ ಮಾಡೋದು
ಇಂಟ್ರೊಡಕ್ಷನ್ ಅಷ್ಟೇ ಅಲ್ಲ. ಓಕೆ
ಸರಿ
ಸರ್, ನಾನು ಶುರು ಮಾಡ್ತೀನಿ. ಎನಿ ಪ್ರಾಬ್ಲಮ್ ಇಸ್ ದೇರ್ ಯು ಕಾಲ್ ಮೀ, ಹೇಳಿ. ಕೇಳಿದೆ.
ಖಂಡಿತ ಸರ್. ಓಕೆ, ಸ್ಟಾರ್ಟ್ ಸರ್.
Good morning, students. So today we will have some discussion on the laboratory concepts in HHM lab, and also some of the basic things in fluid mechanics and hydraulics, applied hydraulics, which everybody should know, because as an engineer, water is one of the main component you are dealing with throughout your life. So civil engineering means nothing but materials and water. So coming to structural engineering or construction technology or geotechnical engineering, whatever it is there, so diversifications are there. So water is one among them. So we will discuss what are the important aspects, why we have to conduct that laboratory, what is the important significance of each experiment. So all those things we will discuss today. So as you know, water is the abundant natural resources available in nature, and it is a gift of God, as I told in the first class. So we have to have a quantitative idea of how much water is available and how best that water can be utilized for the benefit of the mankind. So that is why, in order to have the prediction and the management of water resources in nature, so we should have some laboratory tests in the college, in models, using models. Always we cannot conduct experiments on the prototypes. Prototypes means they are the structures actually built in the field. So in order to have the prediction of the prototypes, we have to conduct model tests in the laboratory, and by using the results of those model tests, we can always interpret the results from the prototypes. So you have studied one topic on model studies in your applied hydraulics subject. So that is very, very important. Not only in water resources, you have in other subjects also, structural engineering, geotechnical engineering. So you have got a lot of model studies there also. So let me take first why we have to conduct all these experiments in your hydraulics lab. So point number 16. So I advise all of you students, please make a note of this, whatever I am going to tell today, because some of them may be there in your Viva questions in the laboratory manual or may not be there. So I am talking in general, which covers almost most of the topics in fluid mechanics and applied hydraulics, as already the topic is quick scan. So I am going to scan it quickly. So whatever you have studied in your third and fourth semesters, basics of FM and hydraulics. Now we can make note of these points. So here, first point I have written, significance of experiments, quantitative measurement of flow of water. Very, very important. So you are going to use Venturi flume, Venturi meter, notches, VS, all those things in your laboratory. Why they are used? They are used to compute the flow, quantity of flow. So that is available in that model. So similarly in the field, we can correlate these values by knowing the value of CD. So this one important coefficient in hydraulics is the CD, coefficient of discharge, which is nothing but the ratio of actual discharge to the theoretical discharge. So the thing is, when you are calculating theoretical discharge, we are going to neglect losses. That is the main difference. When you are calculating theoretical discharge, the equations are derived based on the basic laws of mechanics only, fluid mechanics only. So there, in those derivations, you might have observed that the losses are neglected, whether it is in Bernoulli's equation or any other equation. Losses we are not going to consider. So that is called as theoretical discharge. But if you consider losses, because naturally when there is a flow, there will be loss from one section to another section, whether it is a pipe flow or a channel flow. So those losses should be accounted. 1%, 2%, 10% losses may be there. So those losses should be, loss of energy should be accounted. So when flow occurs from one point to another point, if you consider those losses and if you measure the discharge, that is your actual discharge. So if you take the ratio of actual discharge to theoretical discharge, so that is called as CD. So actual discharge is always less than theoretical discharge. Normally in the laboratory, we are going to measure the actual discharge by providing collecting tanks or measuring tanks. So you'll be knowing the length, width of the tank. A depth of water you can measure using a scale. Then by taking the volume divided by time, you are going to calculate the actual discharge. So theoretical discharge is calculated using the formula, standard formula for that particular device, and take the ratio. So the CD value is always less than 1. Please make a note of that. CD value is always less than 1. So that is one idea. Once you know the CD value of that equipment, then you can use that value in the field to compute the actual discharge in the field by measuring one or two parameters depending on the experiment. That is one thing. Second one is, you can always compute the efficiency of turbines and pumps, hydraulic machines. So last week I discussed about turbines. So output divided by input you can always compute. So to know the efficiency of a particular machine, so then also we have to conduct experiment on the models in the laboratory, turbines and pumps. Third one is, it is very useful in design of pipe networks. See, normally we are going to compute minor losses and major losses in your laboratory. That is, frictional loss is the major loss. So losses due to sudden expansion, sudden contraction, bends, elbow. So all those come under minor losses. So you know how to compute the major and minor losses. Once you know the major and minor losses, that is those coefficients, loss coefficients, we can compute, and using those loss coefficients, we can always design pipe networks in water supply system. So because in the case of a water supply system, you'll be having huge networks of pipes, so which consists of all this expansion, contraction, bends, elbow, everything will be there in that pipe network. By knowing the loss coefficient, you can always compute for the given discharge, of water, what should be the economical diameter of the pipe that should be provided. So that is your pipe network design. So for that, we need to estimate the losses. That is the significance of those two experiments. Next, you are going to conduct experiments on orifice and mouthpiece also. So that is for actually calculating, once again, CD, CC, CV, all those things we are going to calculate in the case of a vertical orifice. But where it is useful? It is useful in finding the time for emptying or filling of a tank or a water bottle. So because normally in the case of orifice, what we are going to calculate? CD means, so a hole, orifice is nothing but a hole made in a tank, which is used to measure the discharge from the tank. Once again, it is CD is nothing but actual discharge divided by theoretical discharge. So once you know the discharge, how much water is collected, you can always compute in the reverse manner. By knowing the CD value, you can always compute the time taken for emptying or filling a tank. So next, model studies, as I already told, to predict the results from the prototypes, we need to have all these model studies. Whatever experiments you are going to conduct it in the lab, they are all model studies, because prototypes, they are all very big. Weir, notch, whatever you take, turbines, pumps, they are all huge in size. They are all the actual structures are prototypes. Since we cannot conduct directly experiments on the prototypes, model studies are considered. So using scale ratios, that is very important. You have learned in your that model studies about scale ratios, different scale ratios using Reynolds model law and Froude's model law. Mainly those two laws are very important for civil engineers because water is involved. For civil engineers, the main fluid involved is water. We are not worried about any gases or other things. So which mechanical engineers, they are worried. So By knowing the results from the model tests, we can always predict the behavior of the prototypes. So this is how I have given 5 points why this lab is very, very important. You have a lot of points, just I am going to brief it. Now let us discuss one by one. I have made some 24, 25 questions from all the topics. So fluid, what is a fluid? First question, what is a fluid? The difference between solid and a fluid. You should know about the concept of fluid. Any substance which can flow is a fluid. So that is a very simple definition of a fluid. Solids cannot flow. Solids only can be moved from one point to another point, whereas fluids can flow. So that is the important, basic important difference between solid and a fluid. That is due to viscosity. So a fluid has got a very tremendous property, very, very important property of fluid is viscosity. Other properties will be there for solids also. So viscosity means a substance which can flow. So that is having some viscosity. That means it is nothing but the resistance. Viscosity is a measure of resistance offered by that particular fluid to the flow. That is simple definition of viscosity. So it exhibits in the form of a shear stress during motion. So whenever a fluid is in motion, shear stress will be exerted in the opposite direction of the motion, and that is the measure of viscosity. So that is discussed here. You see, you can go to this third one now, Newton's law of viscosity. So that is the basic viscous law in a fluid flow. So which states that shear stress is equal to coefficient of dynamic viscosity multiplied by velocity gradient, dV by dy. So this you have studied. So when you are deriving this equation, certain assumptions are made. So what are those assumptions? So it is a laminar flow. So like that, okay? So laminar flow. So there is the assumption, real fluid. We can take it as a real fluid. So there are two terms called real fluid and ideal fluid. Real fluid means it has got very high viscosity. Ideal fluid means very, very low or negligible viscosity. So water is an example for ideal fluid, whereas thick oils, they are all examples for real fluids. So since we are dealing with water, we will discuss mainly about the properties of water. So this is the Newton's law of viscosity. So from this you can say mu is equal to tau divided by dV by dy. So this dV by dy is nothing but the velocity gradient, rate of change of velocity with respect to distance. So this Newton's law of viscosity has been explained by taking two parallel plates, one fixed plate, one moving plate. So that you have studied in your FM. So when you take the velocity at different layers of the fluid between those two plates, it varies like this. Assuming a linear variation, you have the equation like this. And the units of viscosity, if you substitute, tau will be Newton per meter square. So dV is meter per second, dy is in meters. Distance, if you cancel out, you will get Pascal second or Newton meter square second. So Newton per meter square is nothing but Pascal. So Pascal second is the unit of viscosity, dynamic viscosity. This is how you have to derive. Very, very important thing in this fluid mechanics is about units, SI units. We have to always follow SI units. So Pascal second is the unit of viscosity, and another viscosity is there which doesn't involve velocity component, that is called as kinematic viscosity, denoted by nu. This is known as nu. Nu is given by mu by rho. Rho is mass density. So mass density is kg per meter cube. So mu is Pascal second. So Newton is kg meter per second square, and second will be there divided by kg per meter. Just I have shown you how to get this units, SI units. Very, very important. So kinematic viscosity is expressed in meter square per second. And two more units, normally poise and Stokes. Poise is used for dynamic viscosity, Stokes is used for kinematic viscosity, and this is the relation. One Stokes is 1 centimeter square per second, and 1 Pascal second is 10 poise. These things you have already learned. Anyway, I am recalling it. So this is about viscosity. So coming to properties of water, which I told, some of the properties of water you should remember. You should remember it. So I have written here. Whenever some calculation arises with water, so because normally in hydraulics lab we use only water as the main fluid. So for calculations purpose for water, these are the values you should remember. You should remember this. Unless it is given, you should remember. So rho, mass density, 1000 kg per meter cube at STP. We call it as standard temperature and pressure. Actually, all these properties, they vary with respect to temperature and pressure. Slight variation is there, but these are the standard values you are going to take. So specific weight, gamma, 9810 Newton per meter cube. Okay. Then dynamic viscosity of water. So normally it is the value at 20 degrees centigrade. Normally that value is taken. Some books they take 1 into 10 power minus 3. Some books they take 1.005 into 10 power minus 3. So this is in Pascal second. Then kinematic viscosity, same value almost into 10 power minus 6 meter square per second. This is meter square per second. Bulk modulus of elasticity, this comes into picture in the case of that water hammer in pipes. So this is the value of bulk modulus of water. Then surface tension of water, this is the value. So these values, better you remember. So with units, along with units. So these are the properties of, main properties of water. Now coming to the pressure, pressure is a very important concept in fluid mechanics. So in that you have got two types of pressures. One is gauge pressure and absolute pressure. So this question number 2, I am going to tell about that. So you have a very important relation, P is equal to gamma H, hydrostatic law. So P is the pressure at any point in a static fluid. Gamma is the specific weight of the fluid. H is the distance, vertical distance of that point from the free surface. Okay, that is P is equal to gamma H. This law is called as hydrostatic law, pressure law. Okay, so using this, you can convert pressure intensity to pressure head. Here, please note that P is pressure intensity. Its unit is Newton per meter square or pascals. Gamma is specific weight, unit is Newton per meter cube. And H is pressure head. So sometimes pressure is expressed in terms of meters of water, that is called as H. So if you want H is P by gamma. This I explained in the last class when I told about turbines. Okay, so pressure can be expressed in two ways, one in pascals, another one in meters. So this is the relation. Suppose if you want to convert, so here I have given an example here how to convert an atmospheric pressure value. So normally we take atmospheric pressure value as 760 mm of mercury. In terms of mercury, we are going to tell that. Suppose if you want to find out that in terms of water, so what we have to do, we have to multiply that value by the specific gravity of mercury, that also is 13.6. You should remember this also, because mercury is another fluid which is used in manometers in the laboratory because of its various properties. So all those they have explained in the laboratory manual. I don't want to go into detail about why mercury is used and all the points they have got. I have just gone through that Viva questions with answers. So they have done wonderful work. So you can go through that. Along with that, so whatever I am going to tell you today, these are all some additional informations. Some of them may be there, some of them may not be there in your manual. So here, when you want to convert mercury pressure to water pressure, you have to multiply that by 13.6, which is nothing but the specific gravity of mercury. Okay, then you will get so much meters of water. So this is H value actually. This is in terms of H, meters. Then if you want in terms of P, you have to multiply that by 9,810. That is specific gravity of water, gamma, specific weight of water, gamma. So if you multiply that by that, you will get in pascals, Newton per meter square. So these are all same. See, please note that here atmospheric pressure can be expressed as 760 mm of mercury or 10.336 meters of water, or it can be 101.396 kilopascal. All these are same. This is in terms of mercury. These two are in terms of water. Please note that. So I told you about gauge pressure and absolute pressure. What is the difference? So gauge pressure is nothing but the pressure measured with respect to atmospheric pressure as the reference. So what we do is, whatever we are going to measure in the laboratory, all those pressures are gauge pressures. So using manometers, whatever you are going to measure the pressure, normally we are going to measure pressure in venturimeter experiment, in turbine experiment. Okay, so all those pressures, they are all gauge pressures. So that means atmospheric pressure is taken as the datum. With respect to that, pressure is measured. So sometimes pressure may be positive, then it is called as positive gauge pressure. Sometimes pressure may be negative, it is called as vacuum pressure or suction pressure. That means if the pressure at a point is less than atmospheric pressure, it is called as vacuum pressure. So normally in the case of that suction pipe, that is why that in the case of pumps, that whatever pipe is connected to the sump tank, that is called as suction pipe, because suction pressure will be exerted at the bottom of that pipe to suck the water from the sump. Negative pressure will be there. Negative, that means less than atmospheric pressure, that will be there at the bottom of the suction pipe to suck water into the suction pipe. Then impeller will be there, and it forces, so due to centrifugal action of that impeller, so that water will be forced to the delivery pipe, and then it is collected in the collecting tank or the delivery tank. Okay, that is the procedure. So why I want you to tell this is, so gauge pressure can be positive or negative. It can be positive or negative. Positive means above, more than atmospheric pressure. Negative means less than atmospheric pressure. Absolute pressure means it is referred with respect to zero as the datum. Absolute zero or complete vacuum is taken as the datum. So then absolute pressure is always positive. It cannot be negative. So that means pressure at a point can be negative gauge pressure or vacuum pressure also, but the absolute pressure at that point is always positive. Okay, because it is measured with respect to absolute zero as datum. But one thing, keep it in mind, whatever we are going to measure the pressure in the laboratory experiments, they are all gauge pressures. So please note that whether you are using a piezometer or you are using manometer, so they are all gauge pressures. Okay, so that's what I wanted to tell you. Next, very, very important. So in the case of fluid mechanics, we have three fundamental laws. So question number 8, basic laws of fluid mechanics. There are three important basic laws. One is law of conservation of mass, law of conservation of energy, law of conservation of momentum. So these three are the basic laws of fluid mechanics. Very, very important. So using that law of conservation of mass, you can derive that continuity equation. So one-dimensional continuity equation you have derived. Q is equal to A into V. Discharge is equal to area of flow multiplied by the velocity of flow. So that is continuity equation. So next, energy equation, Bernoulli's equation, law of conservation of energy. So total energy at a particular section remains constant. Very, very important equation in fluid mechanics. Whenever there is a flow, you have that Bernoulli's equation. Whether it is in channel flow or pipe flow, Bernoulli's equation is the fundamental equation which we are going to use for any derivation. Whether you take Notch equation derivation, Weir equation derivation, or Venturi meter, anything. So any flow equation is governed by that Bernoulli's equation. So total energy at a particular section. That means total energy means it consists of three things. One is datum head, another is pressure head, third one is velocity head. So three things will be there. Datum head is denoted by Z. See, I have written here above. So Bernoulli's equation is this: Z1 plus P1 by gamma plus V1 square by 2G is equal to Z2 plus P2 by gamma plus V2 square by 2G. What is the meaning of that? So here the meaning of that is, so datum head is denoted by Z, P by gamma is pressure, energy, then V1 square by 2G is the kinetic head or velocity head. The sum of these three remains constant at a particular section, but what happens in some of the cases you have to add a loss of head here. There will be loss of head, but Bernoulli's equation is derived based on the assumption that there are no losses. If there is any loss, that will be added here. So that is the law of conservation of energy. Third one is conservation of momentum. So last week I explained about this impulse momentum equation, which was used in the case of turbines and pumps. Okay, so what does it say? Impulse of force is nothing but change of momentum. So here momentum is mass into velocity. Impulse of force means F into dt, large force acting over a small interval of time. That is impulse. Okay, so that means in the case of, for example, force of a jet, so force will be enormous, but it is acting over a small time. So that is why F into dt we take. So it is given by d of change in, d means change in momentum of the jet. So mass, m is the mass of the fluid striking, v is the velocity, and change we have to take. So here what happens, if you take this Newton's law, from Newton's law only it is derived. So m into a, so m into acceleration is dv by dt, or f into dt is equal to m into dv. See, so this is how it is derived. This equation is derived from Newton's second law only. So we are dealing with two things in the case of turbines and pumps, or even in the case of impact of jet. That is work done per second, kinetic energy per second. So work done per second is the output, kinetic energy per second is the input in the case of turbines. So I am going to explain you how we got this. So work done is F into U. This I explained in the last class. So force of the jet multiplied by the velocity of that runner or vane. So that gives the work done per second in watts. Newton meter per second is watts. Kinetic energy, we know that per second means it is half mv square per dt. Dt I am writing per second. So how this equation is you are going to get, I am going to tell you. So half into mass is nothing but specific mass multiplied by volume, because specific mass is equal to mass divided by volume. Therefore, mass is equal to rho into volume into v square by dt. So here what I can write here is, once again, discharge is volume divided by time. Please note how I am going to get this. So discharge is equal to volume divided by time, meter cube per second. So therefore, volume will be discharge into time. So q into dt. So this dt and dt will get cancelled. So you'll be left with half into rho q v square. Now what happens? This q can be written as A into V. So that is area of jet multiplied by velocity of jet is the discharge. So A into V. So finally we get half into rho into A into V cube. This is what we are going to use in all the derivations of impact of jet. So whenever we are finding efficiency of jet, this is your input. Whether it is a stationary vane or a moving vane, this is the input or the kinetic energy. But in the case of fixed vane, your output will be 0 because U will be 0. Vane will not be moving, so output will be 0. But in the case of moving vane, in the case of turbines and pumps, everything, so there, this is your kinetic energy per second, and this will be your work done per second. So the ratio of these two gives the efficiency. This is output, this is input. Now in another form, I told on that day, whenever you are using a turbine, so your gamma QH is your input or kinetic energy is the input. So you can have like this also. Half mv square by dt, once again it is rho into volume, once again it is rho into dt, dt will get cancelled. Here what we have to do here is, this half will remain as it is. This rho can be written as gamma by g, because gamma is equal to rho into g, that relation we know, into q, into this v square can be written as 2gh, because we know that v is equal to root 2gh. If you use that Bernoulli's equation, assuming neglecting losses, v square will be 2gh. So if you cancel out all this, you'll get gamma qh. See how it can be derived. So we are going to use directly as input in the formula. How we got it? This is the expression. Here gamma is the specific weight of water, 9,810. Q is the discharge in meter cube per second. H is the pressure head at the entrance of the turbine, which is measured using that pressure gauge in meters. So if you know this, then you can compute the input. Why I told this is, these three are very, very important principles in fluid mechanics. Based on conservation of mass, continuity equation is derived. Based on energy conservation, Bernoulli's equation is derived. Based on momentum conservation, impulse momentum equation is derived. So these are the basic fundamental laws of fluid mechanics, which is used in one or the other experiments. So this is the Bernoulli's equation. This is what I explained there. I have taken two sections here. This is the datum line. Very, very important theorem. Datum line. So center line of the pipe I have taken. So Z1 is the datum head. The datum head is Z1 here. Then P1 by gamma. This is V1 square by 2G. So the total energy or head at any section in a flow has got three terms: datum head term, pressure head term, velocity head term. Here also I have taken another point 2 here. Here also corresponding Z2 P2 by gamma, V2 square by 2G will be there. The sum of these three will be constant. That is the Bernoulli's equation, assuming no losses. Now if you join an imaginary line with joints, these piezometric heads, actually the sum of these two is called as piezometric head. Z plus P by gamma is there, you know, first two terms. This is called as piezometric head. When piezometric head is added to velocity head, then you will get the total head. Okay, so then you will get the total head. Z plus P by gamma is taken as the piezometric head. So when it is an imaginary line, hydraulic gradient line, HGL, it is an imaginary line which joins piezometric heads at different points in a flow. Whereas total energy line or energy gradient line which joins the total energy, including the velocity head or kinetic head. If you take the total head, if you draw an imaginary line, that is your energy gradient line or total energy line. Okay, so this is the Bernoulli's equation. Now we will come to this Venturi-meter, because some points I wanted to tell you in Venturi-meter. So in this experiment, what happens? You have got two sections. One is the inlet section, another is the throat section. The main thing is here, if you want to apply Bernoulli's principle, pressure should vary. P1 and P2, there should be some difference in pressure. There should be some difference in velocity also. So see, at the inlet section, D1 is the diameter, A1 is the area, P1 is the pressure, V1 is the velocity. Okay. At throat, correspondingly, A2, P2, V2, D2, they are the values. Now what happens? At what section pressure is more? That is a question mark now. So to find that, what happens? We will go to from fundamental. Of course, from if you connect the two sections to a YouTube manometer, definitely you will be knowing at what point pressure is more. Actually, pressure is more at the inlet section. You can see here. So whatever liquid is there here, it flows through that. It exerts more pressure at the inlet section. Therefore, it has gone down. So the difference in pressure is nothing but H. That value is H here. Now, why that pressure is more here? That is the question. Why the pressure is more at inlet? Why the pressure is less at throat? Why the difference is there? So what happens here, when in the case of Venturi-meter, the area diameter is gradually reduced here. So this portion is called as converging cone. This is throat section. This is diverging cone. So you have got the values for the inclination and length, all those things. That is available in your manual. So here, since the diameter is more here, area will be more here. Area at inlet will be more. When area is more, velocity is less. Please keep that in mind. When area of flow is more, velocity is less because discharge is constant. Q is equal to A into V. A into V. So when area is more, V should be less. So velocity is less here. When velocity is less, pressure should be more. Why? Because of this Bernoulli's equation. So this total thing is constant, you know. When this total thing is constant, in the case of Venturi-meter, horizontal Venturi-meter, the Z1 and Z2, they will be equal. You can cancel out that. Z1 and Z2, they will be equal in the case of horizontal Venturi-meter. So what happens? In that case, you will be having P1 by gamma plus V1 square by 2G is equal to P2 by gamma plus V2 square by 2G. So if you use that equation, so if V1 is less, P1 should be more. So that is the concept. Velocity and pressure, they are inversely proportional here. So that's why pressure is more here, pressure is less here. And you know, this is the equation we are going to use to compute the actual discharge in the case of Venturi-meter. A1, A2, they are the areas at inlet and throat section. H is called as the Venturi head, okay, which is given by this equation. H into H is this difference, Sm by S minus 1. Sm means specific gravity of the liquid, monometric liquid. Normally, mercury is used. Mercury is used, therefore Sm, specific gravity of that will be 13.6, and S will be specific gravity of the fluid which is flowing through the pipe. Normally it is water. So it is 1. Specific gravity of water is 1. So then what happens here? If you apply this equation there, you will be getting Sm 13.6, S is 1. So 13.6 minus 1, 12.6 times H. That is why we are going to multiply that value by 12.6. So this difference, the whatever difference is there in that manometer reading, that should be multiplied by 12.6 to get the Venturi head. So H is the Venturi head. Once you get that H value, all this you can calculate. By knowing the diameter, you can compute the area by pi d square by 4. So A1, A2 can be found out. So you can calculate the actual discharge. So actually, actual discharge is measured in the collecting tank. So you have to compare this with that. Then you have to get the ratio. So actually, without CD, whatever value you are going to get here, that is theoretical discharge. Theoretical discharge. So CD will be actual discharge divided by theoretical discharge. So that is what that is how we are going to calculate the CD value here. So finding CD value is called as calibration. So finding the coefficients CD, CC, CV, all those things in a laboratory, the term used for that so is called as calibration. Normally, graphical method is used to find those coefficients. So calibration is done graphically. Now, another point here, I have written, see here, D2 is equal to normally 1 by 3 to 3 by 4 D1. What is the meaning of that? That means diameter at throat is normally equal to 1/3 to 3/4 of diameter at inlet. So why that is done? So to avoid cavitation. So I have written in brackets. Why is that? What do you mean by that cavitation? So cavitation means what happens sometimes when you reduce the diameter too much, area will be reduced too much. When area is reduced too much, what happens? Velocity will be very high, very high. When velocity is very high, pressure becomes very less. When the pressure is less than at vapor pressure, when the pressure at any point is less than vapor pressure, then cavitation occurs. So some bubbles will form. So due to that, your discharge capacity will reduce, efficiency of the machine will reduce. So all those CD value will get reduced. So because to avoid all those things, what we have to do is we have to have some value of diameter throat which is between 1.3 to 3 by 4 times D1. So normally we take 50%. So D2 is taken as half of D1. So it lies in between these two. 1 by 3 means 0.33, 3 by 4 means 0.75. So we take normally 0.5. So that's what you can observe in your laboratory, diameter of throat and inlet, that ratio will be there. So that is the reason. So cavitation we have to avoid in any machine because it affects the efficiency of the machine. Or when you are calculating this coefficients will be, you are going to get very, very less value. So normally in the case of venturimeter, CD value lies between 0.9 and 0.98. So losses are less. When the value of the coefficient approaches 1, more than 0.9, we can say that losses are very, very less. So such instruments are more used because we can have more efficiency and more discharge can be obtained. So the meaning of if CD value is very high means 0.98, 0.99, like that means your discharge, actual discharge is almost equal to theoretical discharge. So this is the concept of venturimeter, which works based on Bernoulli's theorem and continuity equation. Calibration of venturimeter we have done in the laboratory. This is what for one experiment. Let me explain that. Normally, the discharge equation is written like this. This is the discharge equation in the case of venturimeter. So this entire thing, except this h to the power half, this entire thing, including CD, can be taken as constant. So that I have taken it as K. So what happens? You can write the equation like this. Q actual is equal to K into h power n, where n is half, 0.5. So this only this term. Suppose if you want to find CD value, if you take only this term, A1, A2, root 2g divided by root of A1 square minus A2 square, that I will take it as K1. I will take it as K1. So CD into K1 into h to the power of half. Now, consider this equation. You take logarithm both sides. Log QA is equal to log K plus n log h. This is the straight line equation form. See, y is equal to mx plus c. If you compare these two, this is y, log QA is y, log K is c, m is n, log h is x. So y is equal to mx plus c represents a straight line with slope m, y-intercept c. So if you compare that, if you draw a straight line, if you take the readings in the laboratory, actual discharge reading and H reading. H reading is obtained by, I told you know how to get that capital H, 12.6 times small h, and plot it on a logarithmic scale. Why we have to use logarithmic scale? Because the range of values of H and Q, it is very high. When the range of your readings is very high, then you have to go for logarithmic scale. For example, one reading is 0.005, another reading is 0.01, another reading is 0.2. See, they are varying too much. So if 10 to the power of -1, -2, -3, like that, if the reading comes in any experiment, then we cannot plot the graph on a plain graph sheet. You have to go for a logarithmic sheet. So take log sheet, plot QA along y-axis, H along x-axis, join the points by a best fit line. So this is very important. So when you are joining the points, all the points won't come along on the same line. So we have to draw a best fit line. That means most of the points should come close to that line. That is called as best fit line. Join a best fit line, then try to get the slope of that, and using that n value becomes the slope here, 0.5. So draw a best fit line in such a way that its slope is 0.5. So that is one method. Okay, draw a line, best fit line whose slope is 0.5, then take the value of this QA at h is equal to 1. So wherever that line cuts that h is equal to 1 line, then at that point, whatever value of QA is there, that itself becomes your K value, because from this equation, if you put h is equal to 1 here, log 1 becomes 0, log QA is equal to log K, so it becomes QA is equal to K. So that is the value of K. So QA is equal to K at h is equal to 1. Then from that, once you get K value and K1 value, CD is given by K divided by K1. Because from this equation, K is nothing but CD into K1. I have written here. So therefore, CD is equal to, so QA divided by K is, this is K. Please make a note of that. This is K into h to the power of half. Okay. So that means once you get the value of K and K1, K1 is this. Please note that this is K1. This is K1. So this is K1. So QA is equal to CD into K1 into h to the power of half. Correct. It is correct. So once you get this h is equal to 1, so then QA is equal to K1. This QA is K1. So K and K1, if you know, you can take the ratio that gives the value of CD graphically. So this is known as calibration. You have to do like this only. So you can compare this value with your analytical calculations. That means analytical calculations means in this experiment you are going to vary the flow. So for different pressures. So pressure will vary. When pressure varies, your h value will differ. Small h value will differ from one trial to another trial. Then capital H will differ. Calculate the theoretical value for that capital H using the formula. Then using the collecting tank, note down the actual discharge, take the ratio. QA by Q theoretical is your CD value. That is analytical method. Compare, take the average of 4 or 5 trials value, CD value average. Compare that with this calibrated value. That means graphical value. Almost it will be same. So the value of CD lies between 0.9 to 0.98 in the case of venturimeter. Why I explain this is the same thing applies in the case of major losses in pipes for computing friction coefficient of friction. Okay, and also in the case of triangular notch. In the case of triangular notch also same thing. For finding CD value, we have to use this calibration technique. Only difference is there, this n value will be 2.5. So same graph is plotted there also in the case of V notch. I think I have given here. I will just show you. In the case of V notch, also, see, this is the triangular notch. Yeah. In the case of triangular notch, same equation. That means only this is the equation. So here also h to the power of 5 by 2 will be there. So n is equal to 2.5. We have to join the points by a slope of line, best fit line of 2.5. And same procedure is followed here also. K by K1 gives the value. And here also the value of CD, here the value of CD lies between 0.6 to 0.65. Okay, in the case of triangular notch. So this is the value of CD. So in notches, losses are more. That's why you are going to get less value of CD. So if CD value is less means losses are more. That is the meaning. Now this is about the venturimeter concept. Now question number 7, flow measuring devices. So what are the different flow measuring devices in your laboratory? So these are all the flow measuring devices: venturimeter, orifice meter, pitot tube. Pitot tube may not be used in the laboratory. So these are the flow measuring devices. In pipes, if you want to measure the flow, these are the instruments used. In channels, if you want to measure the flow, these are the instruments: venturi flume, notches, wears, standing wave flume, all those things. All the equations, discharge equations derived for all these devices, they are based on continuity equation, which is this, and Bernoulli's equation, which is this. So combination of these two will give the equation for discharge for all these devices. Okay. So next, coming to what are the various coefficients? As already told, coefficients means the ratio of actual to theoretical. So keep that in mind. Actual to theoretical is the coefficient. You have got, of course, in your laboratory, you are using mainly three coefficients: CD, CV, CC. Mainly in the case of orifice, vertical orifice experiment, we need to calculate these three coefficients. What is CD? As already told, it is ratio of actual discharge to theoretical discharge. Please make a note that always actual discharge is measured in the laboratory using a collecting tank, whereas theoretical discharge is calculated using formula. So which is derived from that basic concepts of laws of mechanics. So if you take the actual divided by theoretical ratio, it is called as coefficient. So you have three coefficients: CD, CV, CC. CV is actual velocity to theoretical velocity. So theoretical velocity is root 2 GH. If you know the H value, pressure head value at flow, then you can calculate VT as root 2 GH. Okay. Then CC is coefficient of contraction. Coefficient of contraction is nothing but once again actual area divided by theoretical area. Actual area means it is area of jet at vena contracta. This coefficient of contraction we are going to use in the case of orifice, vertical orifice. So there is a relation between these three. If you want CD, CD is equal to CC into CV. That means in the experiment, we can find out only these two using the experiment. This is obtained from this equation. So what I wanted to tell you is coefficient means it is the ratio of actual to theoretical. Anything. It can be discharge, it can be velocity, it can be area, it can be energy. So that is called as coefficient. Please keep that in mind. Always it is less than 1 because if always actual will be less than theoretical, because when you are deriving any equation for theoretical value, we are neglecting losses. So that's why we are getting 100%. If you are considering losses, which is there in actual practice, then you have to deduct those losses. Your coefficient will be less than 1. So VA is less than VT, like that. That's why VA is taken as CV into root 2 GH or CV into VT, like that. QA is taken as CD into QT, like that we have to take. CC is equal to area of that at vena contracta. Area of vena contracta is equal to CC into AT. AT is area of orifice. So if you know the diameter of the orifice, theoretical area you can compute. So this is the various coefficients used mainly in the case of orifice experiment. In other experiments, we are finding CD value. Now, next point is coming to the 10th question, turbine. So this thing last week I have explained, but I saw in the manual, this is the equation given for calculating the output of turbine. In Kaplan turbine, this is the output. So because the energy meter reading we are going to take for computing output, because what happens here in the case of turbine, hydraulic energy gets converted to electrical energy. So here gamma QH, see here, gamma QH is the input, kinetic energy of the jet, that is input. This I explained just now how to get this, starting from half mv square kinetic energy expression, how you got this gamma QH. So gamma is in Newton per meter cube, Q is in meter cube per second, H is in meters. If you multiply these three, you'll be getting Newton meter per second. That is nothing but your watts. Okay. Now this is input. Now output is, you have used this equation in the manual. How you arrived at this equation, that you should keep it in mind. Here in the reading, we are going to take the time for 5 revolutions of the energy meter disk of the. So output is measured by noting down the energy meter disk reading. In the case of turbine, this becomes the output. In the case of pump, this becomes the input. This becomes the output. That is the reverse. Okay, in the case of pump. So 5 is the number of revolutions of that energy meter disk. EM is the energy meter constant. So in your, I think manual, it is given as 1500 revolutions per kilowatt hour. That is the unit for energy meter constant. The meaning of that is, if you apply 1 kilowatt hour power, you can have 1500 revolutions of the disk. That is the meaning. Now, here for 5 revolutions, corresponding energy meter constant is taken here. multiplied by 1000, 60, 60 divided by 736 into T. How you arrived at this, that I have written here. See here, if you observe here, this is in revolutions. 5 is in revolutions divided by energy meter constant is in revolutions per kilowatt hour. This is the constant value. Kilowatt hour can be converted into watt into second. Kilowatt means 1 kilowatt is 1000 watts. That's why this is in the denominator, you know. Denominator of the denominator comes to the numerator. That's why kilowatt conversion to watt is 1000. It comes to numerator now. 1000. Hour to second conversion is 60 into 60. 60 seconds, 60 minutes and 60 seconds. Divided by time has come here. Number of revolutions divided by time into 736 is the conversion factor from HP to watts. That's what I told. In some books they use 736, some books they use 746. So 1 HP is 736 watts. That is the conversion factor we are going to use. So if you substitute these units here, you will get watts only. Just see how we can get watts. So here revolution per revolution will get cancelled. Kilowatt hour will go to numerator and it becomes watt and second. In the denominator second is there. So this second and second will get cancelled. Revolution get cancelled. You will be getting in watts. So the value you are going to get in watts, then when that is divided by 736, you will get in HP. Normally, power of the pump is expressed in HP. That's why this unit is taken. So this is how we have to analyze how that formula has been derived. So interchange these two, you will get for pump. Input for pump is this. Output for pump is this. So take the ratio of output to input, that gives the efficiency. Now last week I told you about different types of turbines. A question may be asked, so how do you select the type of a turbine? So based on specific speed and head value. Very important, because whenever some site conditions are there, so you should judge which type of turbine. That is the work of an engineer. So data you have, but which type of turbine is better suited for that condition, that you have to decide. So based on the head, pressure head, that is the pressure available at the inlet of the turbine. So if it is more than 300 meters, high head, it's a high head. Then specific speed value, see, very important thing here is most of the students do mistake here. Specific speed, this is the formula. N root P divided by h to the power of 5 by 4. Actually, some books, they don't give any unit for specific speed. It's just a number. You follow that one only. But you have got SI system and MKS system. Both you have got for specific speed. So your values will be different. Now, whatever values I have written here, they are for SI system, because we are following now SI units only. If you are following SI units, this P should be in kilowatts. Please note that. Very, very important. It should be in kilowatt. P should be in kilowatt. N should be in RPM. H should be in meters. Then whatever value you get, that is your specific speed. N is the speed of that runner, which you can measure using tachometer in your laboratory, or you can use that digital display also. Then P is the kilowatt power, output power, divided by H is the inlet head. Okay, headed inlet or pressure headed inlet. So this is the formula. It gives a number. Based on that number, you have to decide the type of the turbine. When P is expressed in horsepower, that's what I wanted to tell. Here P is expressed in kilowatt. Then you have got SI unit. When P is expressed in horsepower, then you are going to get in MKS unit. Specific speed value in MKS. So there is a difference, you know. So 1 HP is equal to 0.736 kilowatt or 736 watts. So if you use that value here after converting, then you will get some another number for specific speed, that is in MKS system. Whatever values I have given here, that is in SI system. So if you have got for that data of N, P and H, specific speed value lying between 8.5 to 47, then you can go for Pelton turbine. Once again, this is an arbitrary value. Some books, there may be some changes. So 8.5 to 50, some books they give. Okay, that is based on your decision. You can decide like that or like this. So because lot of experiments have been done. So whenever you want to give some universal concept, you have to do lot of experiments. In the laboratory, you are doing only some 3-4 trials, but in practice, to derive all these conclusions, they are based on thousands of experiments conducted on different types of turbines. Then only they can arrive at these values, including your code books. IS 456, IS 800, how they are developed. How they are developed? They are developed by conducting tremendous number of thousands, lakhs together number of experiments with different proportions and all. That is the work behind that code. That is why in India, almost 15 years, 20 years it will take to develop a new code. You might have known. So 1978, IS 456 was there. After that, after 22 years, in 2000, it was revised. So we are following that 2000 code only, IS 456, 2000. Now in steel also, 1984, IS 800 was there. Now it was revised in 2007. So that means almost it took how many years? To 23 years for revising the code. Now we are following the 2007 code like that. Like that here also, in hydraulics also, lot of experiments have to be conducted. Then only you can come to a conclusion. Oh, okay, this can be followed. There's a guidelines. This is only a guidelines. There's no hard and fast rule. So that's why I told it is arbitrary. So if the head value lies between 150 to 300 meters and specific speed value like between 30 to 85, so like slightly higher than this, then you can go for either Pelton or Francis. Then 60 to 150, this is the range, head. And specific speed higher than this, you can go for Francis. Medium head turbine is Francis. Medium head, medium specific speed. Then if the head is very less and if the specific speed is more, then you can go for Kaplan. So Kaplan is a low head, high discharge, high specific speed turbine. Whereas Pelton turbine is a high head, low discharge, low specific speed turbine. That is the difference, okay? And Pelton turbine is an impulse turbine. Kaplan turbine is a reaction turbine. So in the last class, I explained about those things. Now, one important characteristic curve of turbine you should understand is this operating characteristics. Operating characteristics means speed of the turbine is kept constant. So you are going to conduct experiment on constant speed and we are going to plot the characteristics. So mainly we plot output and efficiency in that. So efficiency curve versus discharge. So efficiency curve, it goes like this, it increases, then it reduces. So some peak value will be there. That is the point of maximum efficiency. Then similarly output also increases. But initially you should have some minimum discharge to start the motion of runner of the turbine. That is your Q0. So it won't start from here, it will start from here. So here output is given by this. Just now I explained how to get this. Input is given by this, the ratio is your efficiency. Now this is a very important experiment where maximum efficiency of the turbine is obtained, and normally this value of Q is taken. This value of Q is taken, that is called as the design discharge. Design discharge for the turbine is the discharge at which maximum efficiency can be obtained. Even in the case of pumps also, it's the same thing. So this, of course, this graph you will be drawing in that operating characteristics of performance characteristics of turbine. Main characteristics means you have to take H constant. Then you take H is equal to constant, head constant, and if you conduct the experiment, they are called as main characteristics of the turbine. It has been neatly explained in your manual, very neatly. You can follow that. Just I want to tell you about why the importance of this efficiency, eta max. Now coming to pumps, main things you should keep it in mind is what do you mean by total head acting on a pump? So total head acting on a pump consists of three parts. One is HS, HV, HL. So this HS is called as the static head. Static head is nothing but your whatever reading you are going to get in the suction pipe and delivery pipe, sum of those two. That means reading obtained from the suction pressure gauge and delivery pressure gauge, total. So total reading, that is called as your static head. And you have one other called velocity head or kinetic head, V square by 2G, HV. So where V is the velocity in the delivery pipe. So how to get velocity in the delivery pipe? that is discharge measured in the collecting tank, divided by area of delivery pipe. Okay. So area of delivery pipe is A I have taken. So V square by 2G is your HV. So add these two. In addition to that, you'll be having frictional losses. Normally, major loss only is considered. So 4FL V square by 2GD, where F is called as the coefficient of friction. If you want to consider minor losses also, expansion, contraction, bend, all those things, if they are there, you should have corresponding loss coefficient values. You can add those values also for minor losses. So 4FL V square by 2GD, you see it is calculated for both the suction pipe as well as for delivery pipe. So velocity, you have to take corresponding velocity in suction pipe, corresponding velocity in delivery pipe. For that, Q by A is the formula for finding velocities. So L is the length of the pipe, suction pipe and delivery pipe separately you have to take. F is the coefficient of friction of the material of the pipes separately. Okay. D is the diameters of suction pipe and delivery pipe. So this term has to be calculated for both suction pipe as well as delivery pipe, and they have to be added. So this is called as the total head. So this H value is used to compute that output, gamma QH. In the case of pumper, gamma QH becomes the output. So Q you can measure in the collecting tank. H is obtained by adding these three. Then gamma you will be knowing 9,810 Newton per meter cube for water. So if you multiply all those three gamma QH, you are going to get the value of output in watts. So input you can measure using that energy meter reading, as I already explained in the case of turbine. So then take the ratio. Now if you plot the operating characteristics of pumper, so you will be getting like this. So one important difference between turbine and pump is here. It lies here. In the case of pumper, you can see efficiency increases, then drastically it reduces. Whereas here, it is not much. Okay, see the curve, efficiency curve. And another graph is very important in pump is head versus discharge. So you can observe, it's a curve actually, it's not a straight line. So your head decreases with the discharge. Head decreases with discharge. Why this graph is very, very important is, once again, here also we have to compute the maximum efficiency. Eta O means overall efficiency. It takes into account all the losses. So overall efficiency, what happens at this point, it is maximum. Draw an ordinate at that point to cut the x-axis, which measures discharge. Y-axis H and eta, x-axis discharge. So this point where maximum efficiency occurs, this discharge, whatever we are going to get, it is called as the design discharge. So design discharge of a pump is nothing but the discharge at maximum efficiency. Similarly, design head, we call it as design head. What is design head? Now here you take at the same this thing, wherever this line cuts this H, please note here, wherever this line cuts this H graph, H versus Q graph, at that point you draw a horizontal line here. It cuts somewhere here. It cuts somewhere here, the axis, H axis. So that value of H is nothing but your design head. That means design head and design discharge in a pumper, they are at the point of maximum efficiency. Whatever discharge is there, whatever head is there, at the point of maximum efficiency, that is called as your design head and design discharge in the case of pump. So that is why this operating characteristics of pumps, they are very, very important. Similarly, in this case also, main characteristics is done for H is equal to constant. Okay. In the laboratory, we are doing experiment for both the things, constant speed as well as constant head. So this is about turbine and pump. Now we'll come to another important concept, Reynolds number and Froude number. Very, very important. You should know the difference. What is Reynolds number, where it is used? What is Froude number? There are so many dimensionless numbers in hydraulics. You have Mach number, Weber number, Euler number. Okay, but mainly we are going to use these two. Reynolds number, it is the ratio of inertia force to viscous force. Definition is that. So whenever the fluid is flowing, it has got some inertia force, mass into acceleration. That is your inertia force. Mass into acceleration is inertia force. Divided by viscous force is also there. Viscous force is shear stress multiplied by the area. That is viscous force. So if you take that ratio, inertia force to viscous force, and if you simplify, you are going to get an expression like this, rho Vd by mu. In the case of a pipe flow, what is rho Vd by mu? So rho is the specific mass of that liquid. Normally we are taking water. So rho is 1000 kg per meter cube. Velocity can be measured by knowing the discharge, Q divided by area of the pipe. Discharge divided by area of pipe gives the velocity. D is the diameter of the pipe. Mu is the dynamic viscosity of water, which I have given. At the end, I have given 1.005 into 10 power minus 3. That is the value in SI units. That value you have to take if you substitute in this. So V should be in meter per second, rho should be in kg per meter cube, D should be in meters, mu should be in Pascal second. Then if you substitute here and simplify, you'll get some number. Because it's a ratio, it's a number. Ratio of force to force. Inertia force to viscous force, you will get a number. So depending on that number, you can classify the flows like laminar and turbulent. If the number is less than 500, it is a laminar flow. If the number is greater than 2000, it's a turbulent flow. In between these two, if it lies, it is called as transition flow. Transition flow. So that is where you are. If you want to design a pipe, Reynolds number concept is very important in deciding about the losses and design of pipe. That is very important. In pipe flows, Reynolds number plays a very important role. Depending on its number, you can decide whether it is laminar or turbulent. Normally, laminar flow occurs in the case of real fluids, thick oils, where viscosity is high, you will be having laminar flow. See, in the denominator, you can see viscosity term here. If the denominator is very high, naturally, the value will be less, Re will be less. So if that is why, if it is less than 500, laminar flow means that is for real fluids, thick oils like that. Whereas for ideal fluids, it is turbulent flow, greater than 2000. So for ideal fluid, mu of water is very less compared to the other fluids, thicker fluids. Mu of water is less, it's an ideal fluid. So in that case, mu is less means denominator is less, Re will be very high, so more than 2000 turbulent flow. That is why in the case of water, we have turbulent flow. In the case of thick oils, we have laminar flow. That means it flows in layers, smooth layers. Thick oils, they flow very slowly, smooth layers. Whereas water with a huge velocity and with eddy currents, so turbulence effect, it flows in pipes. That is why it is a turbulent flow. So in your laboratory, if you conduct experiment in minor losses, major losses, and if you find Reynolds number, definitely you will get more than 2000. It's a turbulent flow. This is very useful in the case of pipe flow. In the case of channel flow, another number called Froude number is important. So Froude number is important in the measurement of channel flows. What is Froude number? It is the ratio of gravity force, inertia force to gravity force. So inertia force to viscous force is Reynolds number. Inertia force to gravity force is weight of that liquid. That is Froude's number. So that is mainly useful in channel flow. If the value of Froude's number is equal to 1, it is critical flow. Less than 1, subcritical flow. More than 1, supercritical flow. So this is the concept. Here, it mainly depends on velocity. Pressure won't come into picture here, because pipe flows are pressure flows, open channel flows are gravity flows. So that I will come discuss later. Difference between pipe flow and channel flow I will discuss. So this, based on this value of Froude number, which is the ratio of inertia force to gravity force, we have arrived at the result. By calculating this value, we can classify the flow into critical, subcritical, and supercritical flows. Now, this is what critical flow in channels. So this you have studied in your applied hydraulics. Only I wanted to tell you what are the conditions for critical flow in a channel. Very important concept, critical flow. There are so many advantages of critical flow. So these are the properties of critical flow, characteristics. You have got, suppose you know the discharge. For a given discharge, specific energy will be minimum. What is specific energy? E. E is Y plus V square by 2G. I am talking about channel flows now, open channel flows. Y is the depth of flow, V is the velocity of flow. So if you want the specific energy at a particular section of a channel flow, Y plus V square by 2G is the formula. Okay, so that means it is the total energy referred or energy referred with respect to channel bottom itself as datum. Here datum head won't come into picture. Actually, this is nothing but your total energy. Z won't come into picture here because channel bottom itself is taken as datum, Z will be 0. So Y plus V square by 2G, that is the specific energy. So this energy, if it is minimum for a given Q, then it is critical flow. Discharge is maximum for a given E. Specific energy you will be knowing at whatever value of discharge, specific energy for a given specific energy, if the discharge is maximum, we can say that it has attained critical flow condition. And specific force concept, specific force is given by this expression, Q square by Ga plus Az bar. I have taken an example of trapezoidal channel here. A is the area of flow, Z bar is the distance of centroid from the free surface to that. Okay, Q is the discharge, A is capital A is the area of flow. So if you use this expression, you are going to get what is called as specific force. So this is specific force, this is specific energy. So for specific force, specific energy, they are different concepts. But in the case of critical flow, specific force is also minimum for a given Q, and for a given F, discharge is maximum. So two things you should keep it in mind. In the case of critical flow, Froude number is equal to 1. Therefore, that is V by root GD is there, that is equal to 1. Then where that, what is that D there? D is called as the hydraulic depth, A by T. In the case of channel, D is denoted as A by T, hydraulic depth. A means area of flow, T means top width. Top width means this. So depending on the type of cross section, you can have the value of A and T. So using that, by knowing D, you can compute FR. If FR Froude number value is 1, then it is critical flow. If it is less than 1, it is subcritical. If it is more than 1, it is supercritical flow. If you plot a graph of Y versus E, so depth is plotted here, E is plotted along x-axis, you are going to get a curve like this. This is called as your specific energy curve. You have studied in your open channel hydraulics chapter. So this is 45 degrees line. This is 45 degrees line. So this curve will be, property of this curve is it is asymptotic to the 45 degrees line. It will never meet, but it will be parallel like this. That is the property. So you can see the characteristics of this curve. At this point, you have minimum specific energy. So minimum specific energy. So corresponding to that, whatever depth is there, that is called as YC. That is the critical depth, YC. And if you take any other point E, you will be having two values of depths, Y1 and Y2. They are called as the alternate depths. So at any other value of except E minimum, if you take any other value of E, you will be having two values of depths, Y1 and Y2. Y1 corresponds to supercritical flow, Y2 corresponds to subcritical flow. So that means whatever curve above this point is there, that is subcritical flow. Below this curve, below this line, whatever curve is there, that represents supercritical flow, where FR is greater than 1, here FR is less than 1. Okay, so that is the meaning of critical, subcritical and supercritical flows. And condition, normal condition for critical flow is this. This you should remember, Q square by G is equal to AQ by G. This is the condition for critical flow in any type of channel, whether it is rectangular, triangular, trapezoidal, circular, whatever it is, parabolic, whatever it is. This is the general condition. So this you have derived in your open channel hydraulics chapter. So by for deriving that, you have to take dE by dy is equal to 0, because we know that at critical depth, E will be minimum. The condition for minimum E is dE by dy should be 0. If you do all those derivations, you will get this equation. Q is the discharge, G is 9.81 meter per second square, A is the area, this area of flow, T is the top width. So this is the general condition for critical flow in any type of channel. In the case of rectangular channel, if you simplify this, you will get this equation. So here, this Q, capital Q is nothing but small q into B. This can be defined only in the case of rectangular channel, because it has got uniform width. So width won't change in the case of rectangular channel, whereas in triangle and trapezoidal channels, width will change. So bottom width will not be constant, it changes like this. So in the case of rectangle, it remains same. Therefore, this Q by B, B is nothing but your bottom width. So that gives discharge per unit width. Its unit is meter cube per second per meter, and critical depth in the case of a rectangular channel is given by this equation. If you substitute in this, you will get this. All this you have done in your classroom, in your class, regular class. Okay. Then similarly, if you want to have for rectangular channels, the distribution of velocity discharge, it will be like this. Another graph you should remember is this. If you plot depth versus discharge, so discharge is plotted. Discharge means discharge per unit width, small q, not capital Q. So small q is capital Q divided by B. So if you plot the graph, you are going to get a curve something like this. You can observe that at some point here, Q is maximum, then it reduces. So this point where Q is maximum is the point of critical flow. That means the depth of flow corresponding to that will be YC. That is what this equation gives. Okay, so this is what I wanted to explain in the case of critical flow condition. Then coming to Venturi flow and standing wave flow, this is another experiment which is used to measure discharge in channels. I think only one Venturi flow may be there for you, standing wave flow may not be there. Anyway, just briefly explain you what is that. You might have studied in your theory class also. So Venturi flow, it consists of a inlet portion like this is channel. It's a small channel provided in a laboratory. Inlet section is this, throat section is this. At the throat section, your width is reduced. This is in plan, this is in elevation. Small b is the width of throat, capital B is the width at inlet, and width of the channel itself. This is throat section. Because of this reduction in the throat width, you will be having a, what is that, afflux. Afflux means there will be a change in the depth of flow. Capital H minus small h. So here the depth of flow is h at the throat section. Capital H is at the inlet section. You can measure this using that gauges, hook gauge or point gauge. You can use to measure this capital H and small h. So just by measuring the depth of flow, you can compute the discharge. That is the advantage here in the case of channels by using Venturi flow. This is the equation which is used to compute the discharge in the Venturi flow. Or to calibrate a Venturi flow, CD is equal to Q actual divided by Q theoretical. So except CD, whatever other term is there, that is your Q theoretical discharge, which is derived using the fundamental concepts of flow, Bernoulli's equation only. So Q actual can be measured in the tank or using a notch, whatever is there in your laboratory. So that ratio Q actual divided by Q theoretical gives the value of CD. One thing is here, the velocity at the throat is so designed that it is less than critical velocity. Critical velocity means it is the velocity of flow at critical depth of flow. So VC is the velocity of flow when the flow is critical. Okay, so velocity at the throat is less than VC in the case of Venturi flow, so that there will not be any formation of hydraulic jump. So hydraulic jump will form only if V at throat is greater than VC. That happens in the case of standing wave flow. That is the difference between these two. So this is the equation used to find discharge in standing wave flow. So in standing wave flow, only this B and H you have to measure. So there will be a hump provided here. There will be a hump. In addition to the restriction, the reduction in the width of the channel, a hump is provided here, just to have hydraulic jump formation here. You can see here, this is the formation of hydraulic jump. Because your velocity at throat, it is designed in such a way that velocity at throat is greater than critical velocity, then hydraulic jump will form here. So due to that hydraulic jump, there will be some loss of energy, and you can compute the discharge used by just measuring this H and B. So you can see here, discharge equation consists of only this H and B. So of course, I don't know whether you have got this experiment in your lab or not, but I wanted to tell you the difference between these two flumes. Both the flumes are used to measure the discharge in channels. In Venturi flume, no hydraulic jump formation. In standing wave flume, hydraulic jump formation is there. Now coming to triangular notch, of course, this I have explained when I explained about that, what is that, Venturi meter and this V notch experiments, we have to draw the graphs, log graph, okay. Cipolliti notch, it is a special type of trapezoidal notch in which this side slope is 4 vertical to 1 horizontal, or this angle theta by 2. Actually, this is theta by 2, this is theta by 2. If you add that, you will get theta. So this theta by 2 is 14 degrees. 14, I have not written here. Anyway, theta by 2 is 14 degrees, or tan theta by 2 is 1 by 4. 1 by 4. This is the ratio. Why this notch, Cipolliti notch has got a special property? Why they have provided 1:4 like that? Because the Cipolliti notch, if you want to calculate the discharge for a Cipolliti using a Cipolliti notch, then it is more accurate, because the difference between rectangular notch and Cipolliti notch is that if you consider end contraction, what do you mean by end contraction? End contraction means whenever flow occurs over a notch, so the water sheet will flow like this, will flow like this. Initially, channel will be having some width, then later on that width will reduce towards the notch. You might have observed in the laboratory. So L is the length of the notch here, but if you take channel here, channel width is something like B. So that L is less than B. When there is a contraction in the width of flow, there will be some contraction. There will not be some flow at the corners. So that is called as end contraction. So water flows like this. Water flows like this. Contracted flow will be contracted at the edges. That is called at the ends. That is called as end contraction. Here and here it will be there. There will be two end contractions. This is the formula to find a discharge through a rectangular notch with end contraction. What is that formula? For rectangular notch, the formula is 2/3 into L into h to the power of 3/2 into root Tg. That you know how to calculate the discharge through a rectangular notch. It is there in your manual also. Theory also has studied, you have derived that equation. But if you include end contraction, the difference is 2/3 root 2g h to the power of 3/2. This is common. Instead of L minus 0.2 h you have to take. This accounts for the end contraction, because the general formula is n into 0.1 h, where n is the number of end contractions into 0.1. So here there are two end contractions. Here and here there are two end contractions. So 2 into 0.1 means 0.2. That's why I have taken here. So 2/3 into L minus 0.2 h into root 2g into h to the power of 3/2. That is the discharge equation for a rectangular notch with end contraction, two end contraction. And when that is added with the triangular portion discharge. So actually you have to, when you are calculating the discharge through a trapezoidal notch, you have to add the discharge over triangular notch and discharge over rectangular portion. So that's what I have done here. The first term indicates rectangular portion discharge plus second term triangular portion discharge, 8/15 tan theta/2 root 2g into h to the power of 5/2. So 1 h I have taken outside here because it's 3/2 I have taken common. So this is due to triangular portion. This is due to rectangular portion with end contraction. If you add these two, if you simplify, you will get an equation like this. This is nothing but discharge over a rectangular notch with that means you are taking without end contraction. That means 2/3 L into root 2g h to the power of 3. If you simplify this, you will get this. So that is why Cipolliti is the name of the person who has derived a special type of notch. So one thing is, if you use this formula, directly you can get the theoretical discharge over the rectangular notch. You need not go for trapezoidal notch equation. Rectangular notch equation itself will give the discharge over Cipolliti notch. That is why this has been introduced. You can just try this. Simple calculation is there. If you simplify this, you will get this, and compare this with your rectangular notch discharge equation. They are same. So this is about a special type of notch. So in your laboratory, you are going to do types of flows. Types of flows means you have studied in your fluid mechanics, kinematics, fundamentals of fluid flow. You have different types of flows. In Viva, normally they will ask these questions, types of flows: steady, unsteady flow, steady flow, unsteady flow. So what do you mean by steady and unsteady? So see these flow parameters. What are the different flow parameters? Velocity, pressure, density, acceleration. They are all called as flow parameters. So if the flow properties or parameters, they don't change with respect to time at a particular section, then we call it as steady flow. Steady corresponds to properties won't change with respect to time. Unsteady means if it changes with respect to time, it is unsteady. So that is why in the laboratory, we will wait for some time. So for taking reading, the flow should be steady. Okay, it should not vary. Suppose you are taking a reading in a V notch, you are taking the head reading, depth of flow over that notch reading, head reading using a gauge. point gauge or hook gauge, we have to wait for some time. Immediately it should not, because the head will be varying. There will be some disturbance in the flow. Once it attains steady flow, it won't, once the head won't change with respect to time, at that time you have to take the reading. You have to wait for some time. So all the readings you have to take when the flow is steady in the laboratory, whether it is a pipe major loss experiment or venturimeter experiment, or it is a V notch or rectangular notch. No, we have to, and even in the case of RFIs also, when the head becomes steady, at the time only you are taking the reading of X and Y, that horizontal scale and vertical scale readings you are going to take. So that means steady flow, to attain steady flow is very, very important for taking readings. Suppose in the variable condition, in some of the experiments, we are going to vary the discharge, then we are going to take the readings, then it becomes unsteady. So if the, at a particular section, if you vary the discharge, then it becomes unsteady. Similarly, uniform, non-uniform. Suppose if the properties won't change with respect to some distance, not with respect to time, with respect to distance, then it is called as uniform. For example, you are taking a prismatic pipe. Diameter of the pipe remains same, let us say. It is not a tapering pipe. If it's a prismatic pipe having same diameter from one end to another end, then the flow, you can take the flow as uniform flow. Uniform flow means velocity remains same at different sections of the flow. Okay, assuming no losses. If some frictional loss is there, we have to account for that. So otherwise, you can take it as uniform flow. So if the fluid properties, mainly velocity, won't change with respect to time, with respect to length of flow, then it is called as uniform flow. Otherwise, if it changes, in the case of a tapering pipe, velocity changes. So I think I have given an example here in that Bernoulli's equation when I explained Bernoulli's principle. I have shown a tapering pipe here. See, this is a tapering pipe. Diameter varies here. Here V1 and V2, they are different here. That means it is a non-uniform flow. Please note that this is a non-uniform flow because V1 and V2, they are varying here. So if the fluid properties won't vary with respect to distance, length of flow, then it is uniform. If it varies, it is non-uniform. Best example is flow in a tapering pipe for non-uniform flow. Then one-dimensional, two-dimensional, three-dimensional flow. This is another type of flow. So this is actually based on the, if the fluid property, velocity, I will take only velocity, let us say, if the velocity is a function of all the three coordinates, x, y, z coordinates of the point of flow, that means V is a function of x, y, z. So because in the case of, in the fundamentals of fluid flow, what we do is we are going to assign coordinates for the point just for the analysis to find the velocity, to find the acceleration. That becomes a part of kinematics of flow. To find the energy, all those things become the part of dynamics of flow. So kinematics of flow, dynamics of flow, we are using Bernoulli's equation. Okay. So in kinematics of flow, we are not using any Bernoulli's equation, only velocity and acceleration we are interested, and the path traced by the fluid. That is important. So if velocity is a function of all the three XYZ coordinates of point of flow, then it is a three-dimensional flow. If it is a function of only X and Y, that means Z, it won't vary in the third direction, then it is a two-dimensional flow. If it varies only in one direction, that is only in X direction, if V is a function of only X, f of X, then it is one-dimensional flow. Normally what we do is the analysis of three-dimensional flow is very complex, very complicated. So what we do is we are going to transform the three-dimensional flow analysis to two-dimensional flow analysis. So instead of taking X, Y, Z, all the three, we will convert into only X and Y, and we are going to analyze. That is possible. Simulation of flows is possible in a software, and theoretical background is also there. So anyway, you are going to study, you have studied only 1D and 2D flows in your hydraulics. So you concentrate only on that. Only I wanted to tell you about that 3D flow means the velocity or pressure, whatever it is, it varies with respect to all the three XYZ components. Then rotational, irrotational flow. So some fluids, when they are flowing in pipe or channel, they start rotating about their mass centers. So the fluid particles, if they start rotating about their mass centers, then it is called as rotational flow. In the case of thick oils or real fluids, thick oils and real fluids, they exhibit rotational flow, whereas water, ideal fluids, they exhibit irrotational flow. Okay, so if they rotate about their mass centers, they are called as rotational flows. Only, of course, in your fluid mechanics, since we are dealing with only water, it is irrotational flow we can take. Then laminar and turbulent, that I explained. Based on the Reynolds number, we can classify flow as laminar and turbulent flow. If the flow takes place in the form of layers, smooth layers or laminae, just like in the case of real fluids, thick oils where viscosity is very high, then it is a laminar flow. Okay, if the flow is in a zigzag motion due to eddy formation, then it is a turbulent flow with high velocity. Reynolds number is more than 2000 in the case of pipes, then it becomes a turbulent flow. For normally we have in water turbulent flow only. So all the experiments, whatever you do in the laboratory, you can just check that. So turbulent flow exists in major loss experiment or venturimeter experiment. If you calculate that Reynolds number, it is more than 2000. That is about turbulent flow. So these are the some basic questions they can ask about types of flows. Then sometimes you may, in any problem, you may have to express the pressure of one fluid in terms of another fluid. So you know for example, they will give the pressure in terms of water. They will ask you to find the pressure in terms of oil of some specific gravity, or mercury in terms of mercury. Like that, they may ask how to do that. So it's very important. It's a conversion of pressure of one fluid in terms of another fluid, whatever will be the experiment. So here I have taken the pressure as P. I have considered two liquids here. One is water, another is mercury. So I have taken example also here. S1 is for water, S2 is for mercury, H1 is for water. So gamma 1 H1. So since I have to express the same pressure in terms of another fluid, it is gamma 2 H2. So you will be knowing H1, gamma 1 and gamma 2. You have to find out H2. So now this gamma 1 can be written as gamma W into S1, because specific gravity is expressed as ratio of specific weight of any fluid divided by specific weight of water. That is, gamma can be expressed as S into gamma W. So gamma 1 can be written as S1 into gamma W. Gamma 2 can be written as SW into gamma W into S2. So gamma W can be cancelled out. So S1 H1 is equal to S2 H2. Very, very simple equation you are going to get by simplifying that. So I will take an example here. S1 H1 for water, S2 H2 for mercury. Let us say I have a pressure head in terms of water, 100 mm. I want to convert that into pressure head in terms of mercury. So H1 is 100 mm. So S1 is water, specific gravity of water is S1, 1. Then S2 is 13.6. That you should be knowing. So if you use this formula, you will get pressure head in terms of mercury as H2 is equal to S1 H1 by H2. Substitute to 7.353 mm. So the meaning of this is 100 mm pressure of water is the same as 7.353 mm of pressure of mercury. So that is why mercury is used in manometers. It has got very high specific gravity value compared to other fluids, and it is not easily mixed with water. Okay, and vapor pressure of mercury is very less. So like this, because of these properties, mercury is used in manometers. So by measuring 7.353 mm of difference of mercury pressure, it is equal to measuring 100 mm pressure of water. So you can see the difference there, 13.6 times. That is why you can lift a bucket of water, but you cannot lift bucket of mercury, because one bucket of mercury will be equal to 13.6 times heavier than one bucket of water. So that is the concept there. So mercury is best suited. So it is very costly. You should be very careful when you are using mercury. So when you are using the operating manometer, you should be very, very cautious. The tappings and all, you should be very careful. Otherwise, mercury will spill out. It is very costly. So that is about the conversion of pressure of one fluid in terms of another fluid. And lastly, I wanted to tell you about this pipe flow and channel flow difference. So pipe flow is flow due to pressure difference. So in the case of pipes, flow occurs only due to pressure difference between 2 points, whereas in case of channel flow, it is due to gravity force. Weight of the fluid itself is responsible for the flow in the case of channel flow. Viscous force is very important in the case of pipe flow. Viscosity is very high in the case of pipe flow. Reynolds number is important. In the case of channel flow, gravity force is important. Where due to weight of the water, only it flow. Weight of water only it flows. But viscous force will be there. Slight viscous force will be there. So, but if you take thick oils in the channels, then we have to take up viscous force also. I am talking about water. Please note that whatever I have covered today mainly concerning to water, because it is hydraulics there. Hydro means water, so you are using mainly water. It is an incompressible fluid. Water is an incompressible fluid. Irrotational flow will be there. Okay, so turbulent flow will be there. In the case of water, it is an ideal fluid. Water is an ideal fluid. Viscosity is small. Gravity force is important in case of channel flow. Froude's number is important. Next, flow possible against gravity in the case of pipe flow. That means you can have flow in upward direction also. So flow can occur in the case you can have for example, that pump. In the case of pumps, water flows from downward to upward direction. Okay, in the upward direction. In the case of vertical venturimeter also, you can have discharge from inlet will be below the throat section. So all those you have learned in your theory class. So inlet of venturimeter will be below the throat section in the case of vertical venturimeter. So there also flow is possible. Against the gravity it is possible, but flow is not possible against gravity in the case of channel flow. Only if some pressure exerts, only if you apply some pressure, then only flow can take place from downward to upward direction in the case of channels. Then normally we use venturimeter and orifice meter in the case of measurement of discharge in the case of pipe flows in laboratory. And venturi flume, notches and wears, V notch, rectangular notch, whatever it is there, Cipolliti notch, trapezoidal notch, whatever is there, they are used for measuring flows in channels. So these are the main differences between pipe flow and channel flow. And lastly, I want to tell you about how to write this gauge equation. So many students, they find difficulty in writing this gauge equation for simple manometers and differential manometers. I will give a very simple method how to write the gauge equation. This is very, very important in solving problems, and we are using this conversion, everything in the case of laboratory experiments also. So let me explain with two simple examples, simple manometer and differential manometer. So simple manometer is used to measure pressure at a point in a flow. At a point, if you want the pressure, we are using simple manometer. If you want the difference in pressure between 2 points, then we go for differential U-tube manometer. There are different types of manometers. Just I will cover only these two. Simple manometer is a simple sketch I have written like this. This is a simple manometer. It's a glass tube connected to the pipe. Let us say some liquid is flowing through this pipe. This is the cross section of the pipe. Perpendicular to the paper, we have the length of the pipe. I want to know the pressure at A at this point. The specific gravity of this liquid is S1. Water, if it is water, S1 is equal to 1. If it is some oil, S1 may be 0.8, 0.9 like that. Okay, whatever is given that you take, and this point is connected where the pressure is measured is to be measured. This is connected to a manometer like this. Now you can observe that in this manometer there is a manometric fluid. Normally mercury is used because I told the properties. So manometric liquid is there here. You can see a difference in the mercury levels here between these two limbs. These are called as limbs. So that difference I have taken it as H. This elevation, you can measure all this using scale. So scales are provided to measure all this. X1 is this distance, H is this distance. Now how to write the gauge equation I will explain. I want the pressure at A, PA. This is the pressure at A, this is unknown. You divide that by gamma W. Gamma W is specific weight of water, which is 9,810 Newton per meter cube. So that we can substitute at the end also. So PA by gamma W plus, so H1 is the distance from A to B. So what you have to do is, now PA is the pressure at A. What is the pressure at B with respect to pressure at A? Pressure at B is more than pressure at A because B is below A. Please use the concept that if the point is below the previous point, pressure is added, pressure is more. If the point is above the previous point, pressure is subtracted, so pressure is negative. So we have to deduct it. So here, see here, from A to B, B is above or below A. That means pressure at B is more than pressure at A. So we have to add, plus sign will come, plus this difference H1, X1, and into whatever specific gravity, whatever liquid is there in that portion from A to B, that specific gravity we have to take, that is S1. X1 into S1. Then from B to C, next level is C. So you have to mark these points first. Wherever there is change in fluid, we have to mark that point. So from B to C, C is below B. Once again, we have to add because pressure at C is more than pressure at B. So plus H into this difference, H into whatever specific gravity of fluid is there in this portion, BC portion, that is S2. If it is mercury, it is 13.6. Here, if it is water, it is S1 is 1. Okay. So H into S2, that should be equal to, now we have come to the last point C, that should be equal to pressure at C divided by gamma W. So this point, we have reached this point, this entire thing should be equal to pressure at C, but the C is open to atmosphere. In the case of simple manometer, one of the limbs will be open to atmosphere, one of the tube of the manometer is open to atmosphere. Here C is open to atmosphere. So atmospheric pressure is taken as 0 here. The 0 means reference. That is why it is called as gauge equation. So gauge pressure we are measuring here. Gauge pressure means we are measuring the pressure at any point with respect to atmospheric pressure as datum. So that's why P atmospheric is taken as datum, that is taken as 0. Okay. So RHS becomes 0 here. In the problem of simple manometer, RHS becomes 0. Once this RH is 0, now X1 you will be knowing, S1 you will be knowing, H you know, S2 you know, all these things you know, gamma W you know, everything is known, RHS is 0, substitute the values, get the value of PA. In terms of Newton per meter square, you are going to get the value of PA, pascals. Then you can convert it to kilopascal, divided by 1000, you will get in kilopascals. So why I explain this is very easy to write the gauge equation if you follow this method. Whatever point you want the pressure, to start from that point, you then go to the next point. If the next point is below that point, add the pressure. If the next point is above the pressure, subtract the pressure. Okay. So take the product of the distance multiplied by specific gravity of the corresponding liquid. Then distance multiplied by the specific gravity of the corresponding liquid. If it is simple manometer, RHS, you take last point, pressure, this is open to atmosphere. Therefore, atmospheric pressure is there at C. Atmospheric pressure PC is taken as 0, datum. So PA is found out after substituting all these values. Then you have here this differential manometer. If you want to measure the pressure difference between 2 points, this is what you are using in the case of Venturi meter experiment. Okay. And in the case of turbine also, you will be using this. So whenever you are using, this is the U-tube differential manometer, there will be 2 limbs. So let us take A and B at these 2 points. I want to measure the pressure difference between these 2 points. So tapping is done to these 2 points. Limbs are connected to these 2 points. I have to start from point A. I have to move towards point B. To start from point A, PA is the pressure at A, PA by gamma W. So this is in terms of water we are writing. This is how we get this, all those things, don't worry about that because it requires the conversion of pressure from one liquid to another liquid, all those concepts. But I am only giving you how to convert, how to write the gauge equation, easy method. So plus, if you want to refer the theory behind this, you can refer the textbook. Plus here, once again, from here to here, I will take it as X1. This point, this you can take it as C, this you can take it as D. From here to here, X1 is the distance and S1 is the specific weight of fluid flowing in this pipe, let us say. So X1 into S1. Then here see H. Next point is this point D, CD. Distance between these two is small h. But this point is above this, that's why I have taken negative. Please make a note here. Very important. So this point is above this point, pressure is less. So minus h into S2 I have to take. Specific gravity of the fluid between these two. Then from this point to B, once again B is above this point D. This is D, this is C. So from here to here distance is x1 minus h. Total is x1, this is h. x1 minus h. Since it is above this point, minus I have to take minus of x1 minus h into S1. Same fluid is there here, S1. This is equal to PB by gamma W. Pressure, we have reached the point B now. RHS becomes PB by gamma W. Please note that PB is not 0 here. Just like here, it is not 0. It is in the pipe only, within the pipe only. It is not atmospheric pressure. Whereas here, it is open to atmosphere. PC we have taken 0, but PB not 0 here. Now everything you know except PA and PB. Except PA and PB, you know all the values, specific gravity value you will be knowing. If you know the distances, everything you can measure using scale. In the laboratory, it is setup is there. I have taken example here, water and mercury. I have taken example H is equal to 100 mm. If you substitute in this, you can make out the pressure difference. We are getting for this you are getting 123.6 kilonewton per meter square or kilopascal. That is the reading. So I have given one hint here. Multiply whatever value of H you are going to get here in terms of mercury. The small h will be the difference in the mercury levels in the manometer. You multiply this by 12.6 to get the difference in pressure head in terms of water. Because that Sm by S minus 1 equation is there, you know, that I have explained earlier. So Sm by S minus 1 gives 12.6 there. So don't multiply by 13.6. 13.6 you are multiply when you are converting pressure of one liquid in terms of another liquid. Pressure at a point. Please note that here. Very, very important. Students do mistake here. 13.6 you have to multiply here by taking, if you are converting pressure at one point. If you are converting pressure difference between 2 points from mercury to water, you have to multiply by 12.6, not 13.6. You can see this equation I have derived. Okay, so this is what I wanted to explain you today. Lot of things are there. There is no end, there is no limit for the data. So I have to myself make an end. So some 25 questions, which are, I think most of the experiments are covered. So I have discussed, I explained. Some of you might have noted down. It is very important. I will be very happy if you have noted down, because some of the concepts, if you start reading, it will take a lot of time. So that's why Dr. Vishwanath sir has taken this initiation. Hello.
ಸುರೇಶ್ ನಾನು ಫೋನ್ ಹಾಗೆ ಇಟ್ಟಿರಿ ಸರ್, ನಾನು ನಿಮ್ಮ ಮೈಕ್ ಮುಂದೆ ಇಟ್ಟಿರ್ತೀನಿ. ಸೊ ನಿಮ್ಗೆ ಏನ್ ಕಾಮೆಂಟ್ಸ್ ಕೇಳಿಸುತ್ತೆ?
ಹೌದು, ನನಗೆ ಇಲ್ಲಿ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ, ಅದಕ್ಕೆ ನಾನು
ಈಗ ಹಾಗೆ ಫೋನ್ ನನ್ನ ಫೋನ್ ನ ಇಲ್ಲಿ ಇಟ್ಟಿರ್ತೀನಿ ಸರ್. ನಿಮ್ದು ಮೊಬೈಲ್ ಫೋನ್ ಹಾಗೆ ಇರ್ಲಿ ಸರ್, ಕೆಳಗಡೆ ಇಟ್ಟಿರಿ.
ನಿಮ್ಗೆ ಸ್ಪೀಕರ್ ಆನ್ ಮಾಡ್ಕೊಳ್ಬೇಕಲ್ಲ, ನಾನು ಅಷ್ಟೇ ಅಲ್ಲ.
ಈಗ ನೀವು ಫೋನ್ ಹಾಗೆ ಕೆಳಗಿಟ್ಟಿರಿ ಸರ್, ನನ್ನ ಫೋನ್ ನ ಇಲ್ಲಿ ಮುಂದೆ ಇಟ್ಟಿರ್ತೀನಿ, ನಿಮ್ಗೆಲ್ಲ ಥ್ರೂ ಫೋನ್.
ಓಕೆ ಓಕೆ ಓಕೆ, ಸರಿ ಸರಿ, ಓಕೆ
ಕೀಪ್ ಯುವರ್ ಫೋನ್.
ಓಕೆ ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು. ಸೊ
ಹೇಳಿ ಸರ್. ಅವರು ಸ್ಪೀಕರ್ ಆನ್ ಮಾಡ್ಕೋಬೇಕು ಸರ್, ಸುರೇಶ್ ಸರ್.
ಸೊ ಐ ಹೋಪ್ you learned some of the concepts. So at least some concepts you have learned from this class, so that it will be a very useful one, both for your theory as well as your practical examinations, I suppose. So I thank all of you, those who have joined. So if there are any queries, I am happy to answer those queries. So I will be moving out of the screen now. Yes. 1 second. ಹೇಳಿ.
ಇಟ್ಕೊಂಡೇ ಸರ್,
ಆಯ್ತು
ಸರ್. ಸರ್ ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್. And Shreyas sir to share his experience of listening to this presentation. And finally, our this section is not.
Hello students, please. Hello students, please mute your. Hello students, please mute your microphones.
Suresh sir,
Suhas? Headi. Yes, sir.
isn't your presentation today and the previous
One second. ಸ್ವಲ್ಪ ಬರ್ತಾರೆ ಆಡಿ ಹೇಳಿ ಸರ್, ಹೇಳಿ ಪ್ಲೀಸ್. ಹೇಳಿ ಸರ್, ಹೇಳಿ ಪ್ಲೀಸ್.
Yes, sir. Sir, just you are actually recalling my experience of teaching this group of students fluid mechanics.
Yes.
Previous
Yes.
and just I like to remember Dr. Modi and said, write a book on the
Sure. I was following that only. Sure, correct.
Just I'm just in my just I'm recalling offers. Just the way you have actually presented your presentation today, no, sir. I was literally a student sitting without turning that side and this side, just listening to you.
Okay, thank you.
Very informative, sir. Thank you so much for getting this opportunity to learn intricacies of fluid mechanics and applied hydraulics in addition
Yes.
to the experiment. I request students, if you have any questions, please just ask her. Just unmute your mics and you can ask questions to sir so that he can clarify your doubt.
Students can ask. If you have any queries, you can ask me. I think they will be having some students have shyness to ask.
Vanilla.
Uma,
Yes, sir.
Vanilla, are you there?
share your experience of
Yes,
your
sir.
presentation.
Morning, sir.
Vanilla, ಹೇಳಿ minor, if you have any doubts, you ask.
No, sir.
Yeah, okay,
It
fine.
was
How was it?
clear,
How was
sir,
it? Yeah.
It was interesting, sir.
Yeah, Sarima, good.
Thank you, sir.
Right, ma. Thank you.
You can share your experience, students.
Sagar.
Hi, sir.
Sagar, are you there?
Yes, sir. Hello.
Yeah, Sagar, good morning. Experience ಹೇಳಪ್ಪ ಏನು ಅನಿಸ್ತು? Yeah,
ಚೆನ್ನಾಗಿದೆ sir.
your experience, Sagar.
Hey, it's interesting, sir.
Yeah, very good. It was interesting. ಏನಾದ್ರು ಕಲ್ತ್ಕೊಂಡ್ರಾ ಸ್ವಲ್ಪ additionals
Yes,
apart
sir.
from the class?
Yes, sir. Yes, sir.
Okay. Sorry.
Sagar Devadi.
Thank you, sir.
Did you understand?
Right, pa. Thank you.
Yes, sir. Yes, sir.
But I was like Shatabdi Express. 25 questions I had to cover, that's why. I told the students to note
ಇಲ್ಲ
down
ಸರ್
the point.
ಚೆನ್ನಾಗಿತ್ತು ಸರ್.
Anyway, I will be mailing this, whatever I have written to Sridhar sir. You can collect it for your information.
Yes, sir.
Some 8 pages are there. I will mail it.
Thank you, sir. Thank you.
Soft copy.
Thank you, sir. Thank you.
Have
Akshata.
any queries?
Akshata.
I can take my number
Akshata.
from Sridhar sir and you can contact me.
Yes, sir,
No
we'll do
problem. Night times I will be free after 9 o'clock. Okay. You can call me and
sir.
tell
Good
me
morning,
your
sir.
doubt. No problem for that. You can take my mobile number.
Okay.
Any
Good morning,
doubt is
Akshata.
there regarding any value or this thing, you can ask me.
How was it, Akshata?
Share your
How was it?
It was very clear, sir. The topics were more clear, sir.
Very good. All the basics you were able to at least glance, right? The basics were
Yeah, sir.
totally
Yeah,
covered.
sir.
Yeah. That's how you need to prepare for exams also. You need to just maintain, chalk down only the important points. Around that, you should start studying. So that's a trick for study. Okay then.
Sure, sir.
Okay.
Thank you, sir.
Sridhar sir.
Thank you.
Thank you, ma. Thank you. Sridhar sir.
yes, sir.
Suresh sir.
ಹೇಳಿ ಸರ್.
Sir, it was extremely precise and highly informative. ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು ಸರ್. ಎಷ್ಟು ಬೇಕೋ ಮಕ್ಕಳಿಗೆ ಅಷ್ಟೇ ಹೇಳಿದಿರಾ.
ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು, ಥ್ಯಾಂಕ್ ಯು.
Nice sir.
ಅದು ಜಿಸ್ಟ್ ಹೇಳ್ಬೇಕಲ್ಲ, ನನಗೆ
sir.
ಸ್ವಲ್ಪ ಫಾಸ್ಟ್ ಅನ್ನಿಸ್ತು, ತುಂಬಾ ಫಾಸ್ಟ್ ಹೋಗ್ತಿದ್ದೀನಿ ಅನ್ನಿಸ್ತು. ಬಟ್
ಇಲ್ಲ ಸರ್, ಪರವಾಗಿಲ್ಲ.
ಅದಕ್ಕೆ ಸ್ಟೂಡೆಂಟ್ಸ್ಗೆ ನಂಬರ್ ತಗೊಳ್ಳಿ ಸರ್, ಅವರು ಎನಿ ಡೌಟ್ ಇಸ್ ದೇ ಕ್ಯಾನ್ ಕಾಲ್ ಮೀ.
ಇಲ್ಲ
ಖಂಡಿತ
ಫಾಸ್ಟ್ ಏನಿಲ್ಲ ಸರ್, ಯಾಕಂದ್ರೆ ಅವರು ಫ್ಲೂಯಿಡ್ ಮೆಕ್ಯಾನಿಕ್ಸ್, ಅಪ್ಲೈಡ್ ಹೈಡ್ರಾಲಿಕ್ಸ್ ಮಾಡಿದಾರಲ್ಲ
ಓದಿದ್ದಾರೆ ಅದನ್ನ. ಅದೇ ಎಸ್, ನಾನು ಅದೇ ಅಸಂಪ್ಷನ್ ಇಟ್ಕೊಂಡು ಮಾಡಿದೆ ಅಷ್ಟೇ.
ಇಲ್ಲ ಸರ್, ಸರಿ ಇತ್ತು ಸರ್, ಸರಿ ಇತ್ತು. ಇಟ್ ವಾಸ್ ಆಪ್ ಸರ್, ಚೆನ್ನಾಗಿತ್ತು ಸರ್. ನಿಮ್ ನಂಬರ್ ಶೇರ್ ಮಾಡ್ತೀನಿ ಸರ್ ಮಕ್ಕಳಿಗೆ, ಏನಾದ್ರು ಡೌಟ್ಸ್.
ಖಂಡಿತ ಖಂಡಿತ, ಮೊಬೈಲ್ ನಂಬರ್ ಕೊಡಿ. ಆಫ್ಟರ್ 9 o'clock ಮಾಡಿ, ನೈಟ್ ತೊಂದರೆ ಇಲ್ಲ.
ಇನ್ಸ್ಟ್ರಕ್ಷನ್ಸ್ ಕೊಟ್ಬಿಟ್ಟೆ ಕೊಡ್ತೀನಿ ಅವರಿಗೆ. ಆಫ್ಟರ್ 9
ಆಗಲಿ, ಡೆಫಿನೆಟ್ಲಿ, ನೋ ಪ್ರಾಬ್ಲಮ್.
HOD sir, conclude the session, sir.
Thank you so much on behalf of the yes,
ನನಗೆ ಫಸ್ಟ್ ನೀವು
ಫ್ಯಾಕಲ್ಟಿ ಸ್ಟೂಡೆಂಟ್ಸ್. ಇರ್ಲಿ ಸರ್, ಅದು ಸ್ವಲ್ಪ ಟೆಕ್ನಿಕಲ್ ಗ್ಲಿಚ್ ಆಯ್ತು. ಅವಾಗ ಏನಿಲ್ಲ ಸರ್, ಹುಡುಗರ ಮಾತಾಡ್ತಿದ್ದೆ ಸ್ವಲ್ಪ, ಎಂಗೇಜಿಂಗ್ ದ ಸ್ಟೂಡೆಂಟ್ಸ್.
ಸರಿ ಸರಿ,
ಅಷ್ಟೇ ಸರ್. ವಿಟಿದು ಎಕ್ಸಾಮಿನೇಷನ್ಸ್ ಅದೆಲ್ಲ ಹೇಳ್ತಿದ್ದೆ ಒಂದು 10 ನಿಮಿಷ.
ಹೌದಾ, ಸರಿ, ಒಳ್ಳೇದಾಯ್ತು.
ಓಕೆ.
Excuse me, sir.
Yes sir,
please.
HOD sir, please conclude sir. If Shreyas sir likes to share the experience, Shreyas sir, please share your experience.
Yes sir.
Please experience sir.
Sir, it was very brisk sir. It was just point to point and it was so helpful for the students. For me it was like all the 3 subjects were coming and it was like a revision sir.
3 ಸಬ್ಜೆಕ್ಟ್ ಚೆನ್ನಾಗಿತ್ತು.
ಹೌದು ಸರ್, 3 ಸಬ್ಜೆಕ್ಟ್ ವೆರಿ ಬ್ರಿಸ್ಕ್ ಆಗಿ ಮತ್ತೆ ಕ್ಯೂಟ್ ಆಗಿ ಸಿಂಪಲ್ ಆಗಿ ಕವರ್ ಮಾಡಿದ್ವಿ ಸರ್. ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್.
And the 25 questions, sir, Suresh sir, the 25 questions what you have framed now sir, it is really precise and accurate sir. Those 25 questions will tell us what fluid mechanics and applied hydraulics with experiments is. Very nice sir. Thanks for your actually experience and your to the point make of the presentation slides. Thank you so much.
Thank you.
Excuse me, sir.
Yeah, please.
Please, Osama Khalid.
Yes, sir. Yes, sir. The session was really interesting, and moreover, it was a really valuable session. And sir, I would like to get the PDF of this this session, the PDF which he was displayed on.
Yes, sir,
Definitely.
I will post that.
Sir will give it to Sridhar sir. Sridhar sir will post it to you, Osama.
Okay, sir. Okay, sir. Thank you, sir.
Sridhar sir will post it to you. Maybe tomorrow, but day after, it will be posted to you people.
Okay, sir.
Definitely.
Thank you, sir. Thank you so much.
Yeah, thank you, Pa. Thank you. Suresh sir.
Thank you.
Thank you, sir. Thank you so much. Sir, we'll get back to
Okay
you.
sir, thank you.
We'll catch you up, sir. Sridhar sir.
Yes sir.
Sridhar sir.
Fine sir.
Conclude ಮಾಡ್ತೀರಾ sir? ಮಾಡಿ conclude.
Yes sir, I conclude. Dear all participants and our dear HOD sir and our speaker, our presenter, a great professor, with having, you have seen, there's no point for me to actually explain about sir now, as you have seen sir for 3 sessions, that itself will actually speak about him. And dear students, you are actually, I'm telling you, you are blessed to hear Suresh sir on these topics. So just I will be concluding this 3 sessions started from previous week by extending my great thanks to HOD sir for providing me inputs and resource person also. Sir is actually usually just give the resource person to us. Simply we are going through the almost like rituals. Just thank you very much HOD sir for providing me this opportunity for me to all the faculties, okay, who are actually coordinating and listening, and actually many are there here for providing. This
sir. Thank you.
Conclude the session. Thank you so much.
Sridhar sir?
Sir, Vishwanath sir.
Sridhar sir? ಹಾ ಸರ್ ಹೇಳಿ ಸರ್, ಹೇಳಿ ಸರ್. ಸರ್ ಹೇಳಿ ಸರ್, ಕೇಳಿಸಿದೆ? ಶ್ರೀಧರ್ ಸರ್?
So I just prepared a small Excel sheet, okay, for us, let us do a calculation, okay. Now, when you go back to the PPT, so this is the area, these are the areas, okay. Now, yeah, so already I had written the area, whatever the area which is there, I had written that area. I'll just zoom to the visibility. So whatever the area which is being given from the architect, I place that area. Now let us do a calculation of water requirement for this building. Okay. Now tell me, as this is an office building, how do we calculate the number of persons?
Students, wish you all the best for the interview.
ಶ್ರೀಧರ್ ಸರ್?
Yes, sir, please, sir. Please.
ಸರ್ ಕೇಳಿಸಿದೆಯಲ್ಲ? ಈಗ ಮಧ್ಯೆ ಯಾಕೋ ಸ್ವಲ್ಪ ಇದಾಯ್ತು, ಬರ್ಲಿಲ್ಲ.
ಸರ್ ಸ್ವಲ್ಪ ಅವರು ಸರ್ ಸುರೇಶ್ ಸರ್ಗೆ ಮಾತು ಕೇಳಿಸ್ತಿಲ್ವಲ್ಲ, ಅದಕ್ಕೆ ನಾನು ಫೋನ್ ಆನ್ ಮಾಡಿಟ್ಟಿದ್ದೆ.
ಅಚ್ಚಾ ಅಚ್ಚಾ ಅಚ್ಚಾ, ಓಕೆ ಓಕೆ. ಹಾ ಹಾ ಹಾ. ಸರ್ ಇದೆಲ್ಲ ಅಂದಲ್ಲ ಆನ್ಲೈನ್ ಇಲ್ಲ ಅಲ್ಲ ಸರ್?
ಸೊ ಅದು ಆನ್ ಆಗಿ
ಹಾ ಹಾ ಓಕೆ 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 ಓಕೆ.
ಸುರೇಶ್ ಸರ್
students and faculty, I thank you all for having joined this session, and I wholeheartedly thank Suresh sir. Suresh Vayar was a very good friend of mine. Sridhar sir, ಕೇಳಿಸಿದೆಲ್ಲ? Very good friend of mine and is a very good teacher, and he agreed and he has come forward and he has given us a excellent information on fluid mechanics. Last week it was 2 sessions and today is the 3rd session. All were very informative, very informative and very precise, and I thank all my faculty, Meghna madam, Shreyas, those who are all present today, and all the students who have participated. Students, thank you so much. Though you had test tomorrow, but still you have come here. That shows your interest. I thank you one and all, and thanks for all the feedbacks that you have given today. So any future programs like this, please attend, because we'll be planning and organizing with a lot of backhand work. We'll not just simply throw something on your face. Okay, we think a lot, and whatever is required, only that we'll post it to you. So therefore, any further thing from the faculty side, please respond, and that will be for your good only. Okay, yeah, 2 hours here, you might think that 2 hours hoಯ್ತಲ್ಲಪ್ಪ ಅಂತ, but 2 hours ಅಲ್ಲಿ ಸುಮಾರು ಕಲ್ತಿದ್ದೀರಾ. ಈ ಕಲ್ತಿದ್ದು ನೆನಪಿಲ್ದಿದ್ರು ಅದು ಹೇಗೆ ಕಲಿಬೇಕು, ಹೇಗೆ ನಾನು ಪಾಠನ ಓದುವಾಗ ಹೇಗೆ ಪ್ಲಾನ್ ಮಾಡಬೇಕು ಅನ್ನೋದಾದ್ರೂ ನಾವು ಕಲ್ತಿದ್ದೀವಿ ಇವತ್ತು. ದಟ್ ಇಸ್ ವಾಟ್ ಈಸ್ ರಿಕ್ವೈರ್ಡ್ ಟುಡೇ, and Suresh sir has given excellent information today. I thank him again on all your behalf. Okay, and sir has been very gracious in sharing the material. He'll be sharing it to Sridhar sir, who's the main coordinator for this webinar, and in turn you can contact Suresh sir. He'll in turn give it to you, because it's knowledge, just sharing. Nothing, neither Suresh sir will be losing nor we will be losing. Okay, it's only gain from one person to another person. Similarly, if you have something, you share it with your friends, and all be as a one team. Start sharing your knowledge, and each one of us can grow. Okay, that should be your motto till you complete your 4th semester. I mean, for all the 6th semester, for the 6th semester. Okay, I wish you all the good for your examinations. Prepare in a very serious way. June 15th, 8th semester examinations will be there, and July 1st week onwards, your examinations will come. So meanwhile, attend to this thing, and you need to write the 3rd assignment. So now, if you don't have time, write the test, third assignment test, and then you still have time another 15 days. So slowly sit at home, read and write the assignment. Okay, don't simply copy, because you have enough time. We are not forcing you to give only in 1 week. You can give at the end. Okay, so please write it in all seriousness, read and write, so that will be a preparation for your examinations. 36 questions. If you read and write, definitely closing your eyes, you can score 65 to 70. That's for assured. Okay, because you have that assessment we have shown earlier also for your classes. In notice board also we have put earlier semesters assignment questions and the examinations questions. We have done an assessment. More than 80 marks, these questions only have appeared. Okay, now with all this, let me not take much of your time. I thank once again all my faculty who have coordinated, Meghna, Shreyas, Supraja, and all the fourth semester teachers, Jai Tirtha, then Mahesh, all of them who take, and Caesar mainly for having taken trouble in arranging this, and Google Meet arranging and sending you all the invitations, and falling behind me again and again. Sir, naale ide ನೀವು ಬರಬೇಕು ಅಂತ. I'm a bit lazy, so he'll be pushing me again and again. So hanಗಾಗಿ ನಾನು ಇವತ್ತು ಬಂದಿದ್ದೇನೆ. Right. With all that, I thank Caesar sir and all the faculty.
Thank you, sir.
Hope
Thank you
we'll
so
be
much.
ending this session. Thank you all.
Thank
We'll
you,
end the
sir.
session. Thank you, madam. Thank you. Thank you.
Thank you, sir. Students, you can log out. Wish you all.
Students, please log out. Okay. Yeah, Hemaka Reddy, thank you all.
Students, log out.
ಇದು ಹೇಳ್ಕೊಡ್ತೀನಿ ಬರ್ತೀನಿ. ಒಂದು ಸ್ವಲ್ಪ ಎಫೆಕ್ಟಿವ್ ಬರಬೇಕು. ಇದು ಚೆನ್ನಾಗಿ ಬಂತು.
ನನಗೆ ಕೆಲಸ ಇದೆ. Yes, sir. We both left. No, 9 students more.
9 students more. Okay, sir.
Yes, sir.
ನಾನು ಮಾಡೋಣ.
ಹೋದ್ಮೇಲಿಂದ ಇದು ಮಾಡೋಣ ಅಷ್ಟೇ. ಓದ್ಕೊಳ್ಳೋದು. ಹೇಮಂತ್ log out. Arun, Hemant, Shivkumar, Ravi Kumar, log out and go and study. Yes. Yes, sir. We both left now.
Yes, sir. So thank you, sir.
Thank you so much, sir. ಅವ್ರದ್ದು ಸುರೇಶ್ ಸರ್ದು ಅವ್ರಿಗೆ ನಾವು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಿತ್ತಿಲ್ಲ ಸರ್. ಆಯ್ತಾ ಹೊರಟು ಸರ್. ನಾನು ಅವ್ರ ಜೊತೆ ಮಾತಾಡೋಣ ಅಂತ ಇದ್ದೆ ಅಷ್ಟೇ.